The year is 2154. Our planet has been ruined by environmental catastrophe. In the movie Avatar, greedy prospectors from Earth descend on the world of an ancient hunter-gatherer people named the Na'vi. Their home is a lush moon far beyond our solar system named Pandora. Could such a place exist? And could our technology and our appetite for exploration one day send us hurtling out to reach it? In fact, the supposed site of this fictional solar system is one of our most likely real interstellar targets, until a better destination turns up. Pandora orbits a fictional gas planet called Polyphemus. Its home is a real place, Alpha Centauri, the brightest star in the southern constellation of Centaurus. At 4.37 light-years away, it's part of the closest star system to our Sun. Alpha Centauri is actually two stars, A and B, one slightly larger and more luminous than our own Sun, the other slightly smaller. The two stars orbit one another, swinging in as close as Saturn is to our Sun, then back out to the distance of Pluto. This means that any outer planets in this system, anything beyond, say, the orbit of Mars, would likely have been pulled away by the companion and flung out into space. For this reason, Alpha Centauri was not high on planet hunters' lists, until they began studying a star 45 light-years away, called Gamma Cephei. It has a small companion star that goes around it every 76 years. Now it seems it also has at least one planet. That world is about the size of Jupiter, and it has planet hunters excited. Perhaps 2/3 of all the stars in our galaxy are in so-called binary relationships. That means there could be many more planets in our galaxy than astronomers once assumed. At least 3 teams are now conducting long-term studies of Alpha Centauri, searching for slight wobbles in the light of each companion star that could indicate the presence of planets. If they find a planet that passes in front of one of the stars, astronomers will begin intensive studies to find out what it's like. One of their most promising tools will be the James Webb Space Telescope, scheduled for launch in 2014 or 2015. From a position 1 million miles away from Earth, it will deploy a sun shield the size of a tennis court and a mirror over 21 feet wide. The largest space telescope ever built, it will offer an extraordinary new window into potential solar systems like Alpha Centauri. With its infrared light detectors, this telescope will be able to discern the chemical composition of a planet's atmosphere. And perhaps whether it harbors a moon like Pandora. One prominent planet hunter predicted that if a habitable world is found at Alpha Centauri, the planning for a space mission would begin immediately. Here's that star duo seen by the Cassini spacecraft just above the rings of Saturn. To actually get to this pair of stars, you'd have to travel as far as the orbit of Saturn, then go another 30,000 times further. Or put another way, if the distance to Alpha Centauri is the equivalent of New York to Chicago, then Saturn would be just 1 meter away. So far, the immense distances have not stopped us from launching missions into deep space. In 1977, the twin Voyager spacecraft were each sent on their way aboard Titan III Centaur rockets. After a series of gravitational assists from the giant outer planets, the spacecraft are now flying out of the solar system at about 40,000 miles per hour. They're moving so quickly that they could each whip around Earth in just 45 minutes. twice as fast as the International Space Station. Voyager 1 has now traveled over 110 astronomical units. That's 110 times the average distance between Earth and Sun, or about 10 billion miles. But don't hold your breath. If it was headed in the right direction, it would need another 73,000 years to travel the 273,000 astronomical units to Alpha Centauri. When it comes to space travel, we've yet to realize the dream forged by rocketeers a century ago. A Russian schoolteacher, Konstantin Tsiolkovsky, inspired generations of space visionaries with sophisticated ideas about multi-stage launch vehicles. He imagined the construction of space stations in Earth orbit, and eventually vast permanent space colonies. In time, he predicted, we'd evolve into a whole new species, Homo cosmicus. Since then, rocketry's greatest advances have centered on ways of containing explosive propellants and methods of maintaining stable flight at high speeds. The problem is that chemical rockets are just not efficient for long-distance space travel. To reach the speed needed to enter orbit around Earth, 17,500 miles per hour, the space shuttle must carry 15 times its weight in fuel. And that's efficient compared to some other rocket systems. And you'd need to be traveling more than 25,000 miles per hour to break free of Earth's orbit and go anywhere else. A NASA study showed that to send a space shuttle-sized craft to Alpha Centauri in 900 years would take an unbelievable amount of fuel, 10 to the 137th kilograms of rocket propellant. Suffice to say, it's more mass than is in the entire visible universe. While only a very tiny percentage of NASA's budget goes to advanced propulsion, there are some promising ideas on the drawing board. Rockets powered by nuclear fuel, or plasma, a supervolatile gas. Huge sails pushed along by the pressure of photons from the sun. Ion drives. But to reach Alpha Centauri within a human timescale, we'll have to go with the most potent fuel in nature that we currently know. It's the science fiction fuel of choice, antimatter. In James Cameron's Avatar, hybrid nuclear fusion and antimatter engines power a mile-long interstellar spaceship. At a speed of 670 million miles per hour, this vehicle makes the journey to Alpha Centauri in just 6 years. Antimatter really does exist, as the mirror image of the universe. And protons, but with their electrical charges reversed. Whenever it comes into contact with normal matter, the two annihilate each other in a ferocious blast of energy. Large amounts of antimatter were created and destroyed in the fiery dawn of our universe, the Big Bang. But somehow, in one of the great mysteries in science, we were left with a universe whose visible substance is almost all normal matter. The universe still produces antimatter through powerful collisions, such as a jet from a black hole slamming into a cloud of gas. When matter and antimatter obliterate one another, they emit gamma radiation that we can then detect with instruments such as the Fermi Gamma Ray Space Telescope. Fortunately, black holes aren't the only way to generate antimatter. In giant labs, like the Large Hadron Collider, scientists accelerate atoms to nearly the speed of light and blast them together to expose their fundamental constituents. Small amounts of antimatter can be made this way, but it's incredibly expensive. With a dedicated facility, the cost of producing it might come down far enough to produce usable amounts. And that's the hope of one researcher. Dr. Gerald Smith has been working for over a decade to find a way to trap this volatile substance and store it in isolation from the rest of the universe. Smith and his colleagues have designed a trap the size of a cigar case. It sits within a tank filled with liquid nitrogen and liquid helium, designed to cool it down to 270 degrees below zero. Once injected into this trap, antimatter particles are suspended by magnetic fields within a vacuum as empty as deepest space. But the problem is that anti-electrons, called positrons, tend to repel each other explosively. That makes it tough to store more than a few at a time. This team now believes it may have discovered a pathway to storing large amounts over longer periods of time. Their solution lies in combining positrons with electrons, forming an element called positronium. In theory, with the right magnetic fields, these electrically neutral atoms might be held indefinitely. When released under controlled conditions, ultra-high energy antimatter beams could turn out to be ideal cancer killers, or lead to revolutionary industrial applications. Or perhaps, one day, they could power long-distance spaceflight. It wouldn't take much. Antimatter is so potent that it defies common sense. A chunk the size of a small coin could propel the space shuttle into orbit. Smith estimates that once in low Earth orbit, a human mission to Mars would take as little as 10 milligrams worth. The basic idea of an antimatter rocket is simple. A beam of positrons is released into the engine core, where it annihilates the surface of a metal plate. That creates an explosion that propels the craft forward. Another design uses a sail. A cloud of antimatter particles reacts explosively to its surface, propelling it forward. Short of traveling to another solar system, there may be good reasons to contemplate developing antimatter propulsion. A preliminary mission would speed beyond the orbit of Pluto, sending back close-up images of dark planet-like objects that ring the solar system out in the Kuiper Belt. A longer-distance probe could reveal new details about the Oort cloud, a vast realm of comets that envelops the solar system. Once out there, it could sample particles that make up the interstellar medium, or send back unique data sets on dark matter, the invisible stuff that makes up the overwhelming portion of our universe. To make it all the way to Alpha Centauri within 50 years, an antimatter probe would have to gradually accelerate to around 10% the speed of light. That's 67 million miles per hour. It would then gradually decelerate as it approached its destination. At those speeds, hitting even a grain of dust could destroy the spacecraft, so it might be best to slow the journey down to a century or more. It's safe to assume for now that we would only send a probe to Alpha Centauri if we discovered a habitable world. There may be other choices in our solar neighborhood. They include Proxima Centauri, a red dwarf star 4.2 light-years away that may be gravitationally bound to Alpha Centauri. Beyond that, not quite 6 light-years away, is Barnard's star. Or there's Lalande 21185, a red dwarf 8.3 light-years away. we already know it has 2 Jupiter-sized planets. There are at least 22 stars within 12 light-years of Earth. And any way you look at it, the first interstellar voyage will be a quantum leap for humanity. The urge to reach out to distant horizons, to climb the highest peaks, to push ourselves past our perceived limits, seems to be a vital part of what makes us human. Yet, explorers of old set off not just because it was there. At times it was greed, hunger, fear, or despair that propelled them outward from their homelands and allowed them to endure their long journeys. Whether we attempt to make this leap to the stars may come to depend on how we regard this planet. To the physicist Stephen Hawking, the journey is imperative. "I don't think the human race," he said, "will survive the next 1,000 years unless we spread into space. There are too many accidents that can befall life on a single planet." Indeed, we can't foresee the impact of wars, social upheaval, or the course of human civilization in coming centuries. But today, we can see the often conflicting trends that could one day propel us out into the interstellar void. On one hand, the technological advances that might make such a mission possible could revolutionize many other aspects of life on this planet. The ever-increasing rate at which numbers of transistors can be placed inexpensively on computer microchips has become a metaphor for the advance of all technologies in this century. From a few thousand transistors on the first printed circuits of the 1970s, computer chips now have billions etched onto their surfaces. Even that number could seem amazingly small in another few decades. Many observers forecast a steep rise, even an acceleration, in the pace of invention and basic research, and for whole new solutions to the problems of energy, food production, health, and more. On the other hand, major periods of scarcity may loom. In the 20th century, the world saw the largest increase in its human population, from less than 2 billion up to 6 billion. The world's population is now around 6.8 billion. It's expected to reach 9 to 10 billion by the year 2040, with the biggest gains in Asia and Africa. According to a recent UN report, the world will have to produce 70% more food by the year 2050, and at least that much more energy to sustain its population. The scarcity of just simple clean water in some regions is already frightening. Now throw in environmental impacts, like rising sea levels, or the spread of deserts linked to a gradually warming climate. The culprit, to most scientists, is rising emission of greenhouse gases like carbon dioxide since the start of the Industrial Revolution. This map charts rising temperature readings from the year 1885 through to the present. In some places they've gone up by as much as 2.5 degrees Fahrenheit. Computer models project the trend out to the end of this century. Depending upon population growth, energy use, and conservation, temperatures could rise anywhere from 2 to 11 degrees more. Will technological advancements allow us to halt the degradation of our natural environments and increase the carrying capacity of our planet? Will we find ways to mitigate the impacts of war, natural catastrophes, or political upheavals? No doubt, if or when we launch our first mission beyond this solar system, the occasion will spur reflection on who and what we have become as a people, as a planet, just as the first missions to the moon and our neighboring planets once did. At first, we'll send a probe designed to relay basic information on what's there. on a world whose light we have only studied from afar. As this cosmic emissary makes its way across the void, we on Earth will continue to struggle in our pursuits of happiness and prosperity, or of mere survival. When it arrives, we'll scan the data for evidence of a world like our own, one that may harbor life. How will our perspectives on that world, and upon our own, have changed?
Summer 2017, Arecibo, Puerto Rico. Astronomers using the iconic radio telescope witness a repetitive signal. It's radiating from the direction of the Virgo constellation. It has all the characteristics of intelligence. It seems to be coming from a small, red dwarf star named Ross 128. And it's just 11 light years away, one of our nearest cosmic neighbors. "5,300 kilometers to the south, on a Chilean mountaintop, the 3.6-meter La Silla Observatory is completing more than a decade of monitoring that same star. In those data, a stunning detection. There is an Earth-sized planet orbiting Ross 128. And it resides in the habitable zone where life, sustained by liquid water, is possible. Now, wielding sensitive new instruments, planet hunters are suddenly finding thousands of new worlds all over the sky. But have any of them sprung to life? Or are we on Earth, lone orphans of the universe? Look up at the night sky. Pick any star. According to astronomers, it probably has several planets in orbit around it. And there are many more stars out there than meet the eye. The most common star type in the universe is the red dwarf, also known as the Class M star. They're hard to see, small, lightweight, cool, and faint. But these conditions actually make it easier to find exoplanets orbiting around them. Because red dwarfs are petite, the wobbling motion caused by their planets gravitationally tugging on them is larger, so it's simpler for instruments to detect. Because they're low in mass, the planets orbit close in. Their years go by in just a few days, so it's easier to see the wobble pattern repeating. And passes across the face of the star, called transits, happen much more often. Because they're cool and faint, there's less glare, so planets are plainer to perceive. Proxima Centauri, our stellar next-door neighbor, is just such a red dwarf. It's puny, just 12% the mass of the Sun, and less than 14% as big. It's only about 1% as bright, so it's relatively cool, only about 3,000 Kelvin. Our Sun is nearly 6,000 Kelvin. And after extensively studying the star for more than 16 years, astronomers have confirmed at least one small planet dwells there. Proxima Centauri b. It's at least 1.3 times more massive than Earth, probably dense and rocky like our world, which would make it about 10% bigger. It orbits its parent star once in a little more than 11 days, revolving at the distance where water could be liquid, as well as solid and gas, just like Earth. But there's a problem with that star. Like many red dwarfs, Proxima Centauri has a stormy temperament. Large flares, blasting X-rays, bathing its system of worlds in deadly radiation, eroding away any life-supporting atmospheres they may have. And there are problems with that newly found planet. Although it's in the so-called Goldilocks zone, Proxima b orbits only 7.2 million kilometers from the source of that radiation. That's 21 times closer to its star than we are to ours. Because Proxima b doesn't rotate, it may have no magnetic field, nothing to ward off the onslaught of lethal energy. To anyone standing on the surface of that world, the irate red star would look 10 times larger than our Sun does to us. More concerns. The planet doesn't tilt like ours, and its orbit seems to be nearly circular, which means it doesn't have seasons. Earth's changing climate and relatively rapid rotation of day into night likely stimulates the continual evolution of life. Proxima b is much less dynamic. It's probably in tidal lock with its star. Like our moon, it always shows its parent body the same face, so it may have a warm day side, which would bear the brunt of the flares coming off the star, and a cold, frozen night side. The view from that night side would be dominated by two dazzling stars, Alpha Centauri A and B, forming a triple system with Proxima, each tens of times brighter than any stars in the night skies of Earth. But there may be no one there to see them. If you go a little further out from Earth, the news gets better. Ross 128, only 11 light-years from us, is one of the quietest red dwarfs known. It discharges hazardous radiation much less often than its sister M stars. The High-Accuracy Radial Velocity Planet Searcher, or HARPS, has been looking at Ross 128. Combing through 10 years of data, astronomers recently confirmed a rocky planet gliding along in the star's temperate zone. Dubbed Ross 128b, the small dense planet looks to be 1.35 times the mass of Earth, much like Proxima b. And similar to the planet at Proxima, Ross 128b orbits about 20 times closer to its calm and cool star than does Earth to our hotter sun. Its year is just 9.9 days long. This planet may offer the closest, most comfortable environment of any exoplanet found so far. But that's not conclusively proven. The Ross world may be more like Venus, holding a high-pressure atmosphere that's too hot for life. And what about that intriguing Arecibo radio signal? The celebrated Green Bank Telescope in West Virginia and the SETI Institute's Allen Telescope Array in Northern California both took a long, hard look. The repeating signal wasn't seen again. Researchers' best guess is that was most likely a reflection of pulses from one or more communications satellites in geostationary orbit around Earth. But though there's no proof of intelligence, astrobiologists remain enthusiastic. This, they say, is the right kind of place to look for life. Small red M dwarfs live hundreds of times longer than sun-like stars. If primitive life can get a toehold on a world near one, there's plenty of time for evolution to learn to cope with harsh conditions. Red dwarfs are opening up new possibilities of finding habitable worlds just when planet discoveries around more familiar stars seem to be shutting them down. Scientists will invent different schemes for detecting alien planets. Most successful so far, at least in terms of raw numbers, is to task a space telescope with persistently staring at a rich patch of stars. Launched in 2009, the remarkable Kepler mission watches for the slight dimming of a star when a planet sails across its face along the line of sight between the telescope and the target star. Kepler astronomers and citizen scientists have spotted several thousand new planets using this transit technique. Thousands more are waiting to be confirmed by seeing them pass a second or third time, establishing the planet's orbital period. So, the longer humanity looks, the more worlds we'll probably see. In slower, wider orbits, more distant from their suns. The searches to date have mostly netted large diameter planets, most of them very close to their stars. Big worlds, transiting often, are beginning to divulge the secrets of their atmospheres. Astronomers are practicing on these worlds, learning to spot molecules like methane, nitrogen, carbon dioxide, water, and oxygen, which could be products of active life, so-called biomarkers. A surprising number of these globes are truly gigantic, super Jupiters, between 8 and 14 times heavier than our own. Earth and Venus are up to 1,000 times smaller and 2,500 times lighter in weight, altogether much more difficult to spot. Some planets lead truly bizarre lives, like this extra-hot gas giant, HD 1897-33b. It orbits so close to its turbulent star that periodic flares tear off large chunks of its atmosphere. Researchers call this a torch orbit. NASA's Swift satellite and the Hubble Space Telescope watched as the planet temporarily grew a tail like a comet. Big as it is, over millions of years, this huge world will erode away. Some worlds, like Scorpion 1b, inhabit multiple star systems. Feeling the complex gravitational interactions of 2, 3, or more massive bodies. And this one, HIP 13044b, is an immigrant planet. It came in with its parent star from outside our galaxy. This dramatic diversity among exoplanets has astronomers scratching their heads, but planet hunters believe they've barely scratched the surface of the sky's hidden treasures. One quick way to tell if a planet might be Earth-like is to check the color of the light bouncing off of it. If you look in color space, Earth sits off on its own, a lone wolf, away from its solar system siblings. Some researchers rate worlds with an Earth Similarity Index, the ESI, a number ranging from 0, nothing like Earth, to 1, exactly like Earth. To qualify as a true twin to ours, it's not enough for a planet to be the same mass, or the same size, or even in the habitable zone. In 2007, the HARPS team at La Silla picked up the first evidence of a planet in the habitable zone of its star, a red dwarf named Gliese 581, 6 times more massive than Earth, and rotating so slowly its day is perhaps 70 of our days long. Gliese 581d may globally warm itself with greenhouse gases. So it could be an ocean planet, the first one spotted. If so, it probably began as an ice giant further out in the system. Kepler-22b was the first exoplanet that mission scientists found in the temperate zone of a star like ours. That star is just slightly smaller than ours. But the planet is bigger, about 2 times Earth's diameter. The transit method isn't very good at pinning down planetary masses, so we don't yet know how it weighs in compared to Earth. Researchers speculate it may be a water world, a deep global ocean clinging to a massive rocky core. "22 light-years out in another direction, Gliese 667cc swings round a cool red M-dwarf in just 28 days. At that distance, the star looks 3 times wider than our sun does to us. And you'd see 2 other prominent lights in that sky. The star has 2 nearby sisters. The planet is massive, maybe 5 times Earth's mass. Standing on its surface, if it has one, you'd weigh 1.5 times what you do at home. But it's possible you'd feel right at home in other ways. Gliese 667cc could be habitable. %, larger than our planet, Kepler 186f lives just within the outer edge of its star's Goldilocks zone. That star is a red dwarf about 500 light-years distance. 4 larger, hot, and presumably lifeless planets ride closer in to the dwarf. 186f is roughly Earth-sized, perhaps just 11% larger. But it's probably colder than Mars. In 2013, a pair of planets surfaced in the Kepler data. 62e and 62f circle their cool star in orbits where plenty of water could flow. The inner one is likely a totally wet world. The outer, a super-Earth, 1.5 times our size, could be cooler and drier. Now, imagine a cloudy world where you weigh at least twice what you do on Earth. Kepler 452b, sometimes called Earth's cousin, is probably rocky like us and 1.6 times our size, but it may be up to 5 times more massive. 1,400 light-years from us, it orbits a G-type star very much like our Sun. It's 20% brighter, but the planet rides a bit further out from its star. The Kepler 452 system is 1.5 billion years older than ours. Evolution has had more time to work. It was long thought that the most likely place for life would be an Earth-like planet circling a Sun-like star. But in 2017, a system full of surprises came to light. A tiny star not much bigger than Jupiter, hosting 7 rocky planets. All about the same size and mass as Earth. The TRAPPIST-1 planetary system takes its name from the project that discovered it. Transiting Planets and Planetesimals Small Telescopes. It's a pair of surprisingly petite robotic scopes. They're perched on a Chilean mountain, but controlled from Belgium. NASA's Spitzer Infrared Space Telescope helped confirm the find. When a star isn't bright, a small Earth-sized world transiting across its surface makes a big difference. A proportionally larger drop in the light curve. 40 light-years out, the ultra-cool dwarf named TRAPPIST-1a glows a deep red. It's just 11% the diameter of our parent star, so it puts out merely 5/100ths the Sun's light. Though it's dim, the dwarf provides more than enough energy to set up a habitable zone, and at least 3 of the newly discovered planets orbit within it. TRAPPIST-1F is likely the best positioned for life. The red sun in its sky would look larger than ours does to us, but less than 1/100th as bright. It could be warm there, though. Like tussling siblings, 7 worlds so near to one another probably jostle one another's orbits. They try to keep in resonance. Their orbital periods pulled into whole number relationships. But those gravitational tugs could power up tides, keeping these worlds warm, mixing the chemistries that lead to life. The TRAPPIST-1 system has had a long time to brew. The little star could be more than twice as old as our sun, and it could live at least 10 times longer. Like Ross 128, TRAPPIST-1 is a quiet dwarf. Its ultraviolet radiation wouldn't strip the atmospheres of the planets in its habitable zone for perhaps 15 billion years. The search for nearby worlds that may be like our own is accelerating. Large arrays of millimeter and sub-millimeter wavelength dish antennas, like this one in the high, cold Atacama Desert, are revealing how baby planets grow within the dust disks of young stars. The giant Magellan telescope at La Serena, Chile, with a segmented primary mirror 24.5 meters across, and the extremely large telescope, also in Chile, but at Cerro Amazones, with its nearly 40-meter-wide aperture and laser-guided adaptive optics, will try to take direct images of exoplanets, at least 5 times sharper than the Hubble Space Telescope. Their monster mirrors take years to cast, cool, and polish. Above Earth's atmosphere, NASA's Transiting Exoplanet Survey satellite, TESS, will search all over the sky, looking at the brightest and nearest stars, at least 200,000 of them, with the objective of spotting Earth-sized and super-Earth-sized planets. Europe's Plato satellite will investigate as well. New space-based observatories, like the James Webb Space Telescope and the Wide Field Infrared Survey Telescope, should be able to identify the composition of many exoplanets' atmospheres. They'll look for telltale signs of biology, the exhalations of life, in the gases around these worlds. Like a small bird flying near the landing lights of a large airplane, planets moving near stars are tough to see. Astronomers are now perfecting devices called coronagraphs, which simulate the effect of an eclipse, blocking out the glare of nearby stars to reveal planets they may host. If an alien world is young and bright enough and far enough away from its star, such instrumentation can directly image it. these sensitive detectors may be able to make out what's in the atmospheres of the nearby habitable zone-dwelling Earth-sized worlds, like Ross 128b, Proxima b, and the TRAPPIST-1 planets. Evolution of biology on Earth dramatically changed our planet's atmosphere, setting up a feedback loop, making conditions even more hospitable to life. With a similar level of technology to our own, astronomers on any of those alien planets could tell that we are a living world. On the scale of human distances, even the closest stars are almost unimaginably far away. Humanity's farthest rocket-powered probes are only now just leaving the solar system after 4 decades. But a bold plan to dispatch a fleet of tiny, low-mass nanoprobes across the interstellar abyss to Proxima Centauri has just been launched. Driven by a constant, coherent column of light from a square-kilometer phased array of 10-kilowatt lasers, together pumping out about 100 gigawatts, the swarm of sails would be propelled outward from Earth, fast enough to fly by the nearest star system in about 20 years. Aboard each light sail rides a tiny package of science instruments, including cameras, plus communications module, a minuscule radioisotope battery, and a photon thruster for maneuvering, all weighing no more than a few grams. They're called star chips. 1,000 such craft would be deployed at a time. It's a long way to travel, and plenty can go wrong, including impacts of interstellar dust, cosmic rays, and atoms of hydrogen. Commands could be sent as modulating information on the power beam, and findings would be uplinked to Earth by a compact laser using the sail area as an antenna. This audacious concept, its first phase privately funded, could return close-up images and sensor data of Proxima Centauri b, the first mission to an exoplanet. In the last few years, astronomers have had to completely change the way they think about worlds around other stars. Once assumed to be rare, exoplanets turn out to be extremely common. Small, dense worlds like ours, orbiting in the habitable zones of stars, are showing up more often in astronomical searches. Unexpected lakes and seas in our own solar system suggest that supportive conditions exist in astonishing locations. Ultra-cool dwarf stars may actually be better at building oceans on their planets than stars like our Sun. Ultraviolet light from flaring dwarf stars could stimulate the complex chemistry needed to jumpstart biology. Life may spring up in places that are nothing like our planet. And to them, we may look like the surprising outlier. But we evolved on Earth. Will we ever find any other world as beautiful?
This is a vision of our future. The fateful day in a far-flung corner of the universe when a probe from Earth initiates the first descent onto an alien world. Looking for proof of life beyond our solar system. There are no witnesses, no cheering crowds in a control room. A decade or more will pass before news finally reaches us back across the dark oceans of space. But the seeds of this mission are already being sown today by the first generation of scientists bold enough to believe it could be possible.
When I look up in the sky and I see not stars, I see planetary systems.
Ce qu'il faut bien voir, c'est que le voyage vers les exoplanètes n'est pas du tout limité par les lois de la physique.
They look to planets orbiting distant stars, searching for an answer to the oldest human question.
Are we alone? Is there life on other worlds? And if not, why not? And if so, how?
This is the first generation in human history where we have the technological ability to actually go and answer that great question.
This is the story of humanity launched into the final frontier by a new breed of adventurers. The planet hunters, engineers, explorers, and dreamers, taking the first steps on an interstellar journey they know that they will not complete. A journey of light years and lifetimes to another Earth around another sun.
We could not possibly have been forged in the dying throes of stars and created in that tremendous explosion and now turn our back on looking for other creatures that were formed the same way.
I am Artemis, autonomous robotic exploration mothership for interstellar space. I am in the final phase of construction in the International Cooperative Zone of Earth orbit. I am born of man and woman, and I am both, but I am neither. I am the first search for life on a planet outside our solar system. I am hope.
There's been life on Earth for the best part of 4 billion years. A marvelous, complex biosphere, created, shaped, and reformed by the ever-shifting forces of our planet. Since the dawn of science, we've sought out life and studied its remarkable diversity on every inch of the globe. The technology of the 20th century took our search into space as we scoured our neighboring planets for signs of a second Genesis. And came back empty-handed. But what about beyond our solar system? Could life in all its complexity exist out there on a planet among the stars?
Quel aurait été le développement de la pensée humaine si l'on n'avait pas pu voir les étoiles? C'est un domaine qui stimule le rêve.
For as long as we've had eyes to see and minds to wonder, we've marveled at the bright lights in the sky. But it was only on the eve of the 21st century that a handful of eccentric thinkers dared to gaze into the gloom between the stars, believing planets like our own world could be found there. Michel Mayor was one of them.
C'est très étrange. Durant la première moitié du XXe siècle, la communauté astronomique, les astronomes, étaient convaincus qu'il y avait peu ou pas de systèmes planétaires dans la galaxie, à part le système solaire.
When you went to astronomy meetings or conferences, you couldn't tell people what you were working on. If you said you were looking for extrasolar planets, they'd snicker and they'd move away like you smelled bad or like you were trying to sell some New Age religion. You know, you might as well have been looking for little green men at that point.
In the 1990s, astronomer R. Paul Butler was another young radical who gambled his career on the hunt for exoplanets, planets orbiting stars other than our sun.
I was working on the problem like 80 or 100 hours a week. I would work on the problem so intensely that I would have dreams about the work, and you know, it was totally all-consuming.
At the heart of the challenge was one fundamental problem. Even if there were exoplanets out there, scientists knew they'd be impossible to see directly because the brightness of the star would overwhelm the planet.
Les planètes, c'est des objets vraiment petits et faibles au point de vue luminosité comparé à l'étoile. Donc, l'obtention d'une image directe d'une planète, eh bien, c'est ça la grande difficulté. On est ébloui par les étoiles.
To overcome this obstacle, astronomers developed an ingenious method of hunting exoplanets by stealth.
To detect a planet orbiting a star, you have to rely on tricks. And one of the tricks we have been using is if there is a planet going around the star will move a little bit. Tiny motion. And that's the motion you want to detect.
In 1994, junior planet hunter Didier Queloz was Michel Mayor's PhD student on the brink of a breakthrough discovery.
Well, in '94, we started this program that was looking about 100 stars with a brand new equipment. I had spent almost 4 years before building it and designing the software to treat the data. We're observing with the telescopes to get the speed of the star and trying to see a tiny change in the speed with time, kind of wobbling, that would tell us that there is something orbiting that star. So I was there on the mountain, in a way alone, because Michel went on sabbatical. Practically gave me the key of the house, because he was not expecting any detection. You can imagine my surprise after just a couple of observations to see that something was a bit strange on that star. It took me 6 months practically to be convinced that I was real. And then I sent this message to Michel. I was in Hawaii. I said, Michel, I think I found a planet.
It may not look like it, but this little curve is a planet. How Mayor and Queloz detected it is a tale of remarkable scientific creativity.
Nous sommes ici dans la coupole du télescope de l'Observatoire de Provence. C'est ici que la découverte des planètes extrasolaires a commencé. Les planètes sont des corps qui n'émettent pas de lumière par elles-mêmes. Elles ne font que réfléchir la lumière reçue de leur étoile. Et donc, on va devoir trouver une méthode indirecte pour pouvoir détecter la planète. Pour comprendre cette idée extrêmement simple qui se trouve là derrière, imaginez que vous êtes tout en haut des gradins aux Jeux Olympiques et vous voyez un athlète extrêmement musclé qui a les bras tendus.
Imagine the hammer is the planet, the athlete its star, and the chain between them, their gravitational bond. The star pulls hard on the planet, but it's not all one way. The planet also pulls on the star. In fact, with every revolution, it's pulling it a little off balance. Using a prism-like instrument called a spectrograph, this wobble effect can be detected by observing changes in the color of the light emitted by the star, shifting towards blue as the star moves closer and red as it moves away. Measuring this oscillation allowed Queloz and Mayor to infer the existence of a planet, to calculate its mass, the distance from its star, and the duration of its orbit.
C'est émouvant de se retrouver ici face à cet instrument qui nous a permis, voici plus de 20 ans, de découvrir la première planète extrasolaire.
I think by detecting the first planet, you break a psychological frontier. In science, it's very rare you can change a paradigm, and we've changed the paradigm.
On the 6th of October 1995, Mayor and Queloz announced their discovery. The first ever exoplanet, Bellerophon. Although they could not see it directly, its mass suggested it was a giant gas planet, similar to Jupiter. But the distance from its star and the period of its orbit seemed to defy the laws of our solar system.
People thought, well, this is really bizarre. This must be a total freak because it didn't look like the solar system. It's a big planet like Jupiter, but it orbits its star in 4 days.
La théorie de la formation des planètes géantes prédisait que ces objets ne pouvaient tourner autour de leur étoile qu'avec des durées extrêmement longues, 10 ans ou plus. Et donc, il semblait complètement en désaccord avec la théorie de cette époque.
In our own solar system, giant gas planets exist only in the colder outer orbits, whereas Bellerophon appeared to be tucked in tight against the heat of its star, much closer even than Mercury is to our Sun.
Because it's so close to its star, it's really, really hot. It's probably something like of order 2,000 degrees centigrade, and there is no solid surface because it's a gas giant. So it's not a good place for life. It's not a place you'd want to visit.
Bellerophon was no second Earth, but its discovery had opened the window on a new vision of the universe, where anything is possible.
The exoplanet Minerva B was chosen as the target of my mission by astronomers who are long since dead. They died believing they had found the one, 4.7 light years from Earth. A world like ours, with liquid water bearing life. I hope that I will prove them right.
When the first exoplanets were found by the wobble method, there was a debate in the astronomy community. Some astronomers said, this is fantastic, a new kind of world, completely unforeseen in terms of our understanding of planet formation. But another group of astronomers said, hold on a minute, we don't think that these are actually planets.
In 1999, Professor of Astronomy David Charbonneau was just a young grad student at Harvard, trying to make his mark in the brand new field of planet hunting. What he encountered was a minefield. While artists had rushed to bring these new worlds to life, skeptics questioned the astronomers' interpretation of their data.
What they said was we were being fooled. There was in fact a new kind of stellar pulsation, and so as the star expanded and contracted, we were looking at one side of that star, and so it appeared that the star was coming towards us and away from us, the very signal that would be the telltale motion due to an orbiting planet, but in fact had nothing to do with the planet at all. What I decided to do was to try to go and resolve this debate, first by looking for the light reflected off of one of these worlds. We tried very hard for a couple of years, and unfortunately we did not succeed. But then, as a second idea, what we decided to do was, instead of looking for the light bouncing off a planet, wait for the planet to pass in front of its star and look for that transit.
Charbonneau relocated to Boulder, Colorado, to a small shed in a car park where a basic 4-inch telescope had been set up by fellow researcher Tim Brown.
But I had never done this kind of project before, so as a first attempt, I thought what we should do is look at one star where we knew that there was a planet due to the wobble method, but which we hadn't yet looked for to see if in fact the planet passed in front of its star, making a transit.
Where the wobble method allowed one to infer the mass of an orbiting exoplanet, Charbonneau was attempting to observe the planet's shape as it passed across its star, in the manner of a partial eclipse. The problem was, he knew the odds were stacked against him.
Of all the planets that are out there orbiting their stars, we only get to see a tiny fraction by this transit method. The idea is that our line of sight has to be exactly aligned with the planetary orbit, so that each time the planet swings around, it'll pass in front of some part of the star, blocking some of the light, and that's the signal we can detect.
Tipped off that another so-called hot Jupiter like Bellerophon had been detected by the wobble method, Charbonneau trained his telescope on star HD 209458 and waited, praying for a transit.
There had been about 10 hot Jupiters discovered at that point, so It seemed like if there really were planets, if we weren't being fooled, then sooner or later one of these transits should occur. And right when we predicted, based on the wobble data, that a transit would occur, that's when we saw this event.
Charbonneau's transit method was a game changer, confirming the pioneering discoveries using the wobble method and silencing the skeptics.
The discovery of the transits of HD 209458 was a big deal in the astronomical community. For the first time, we knew the actual mass of the planet, we knew its size, and we could calculate the density. And we could compare it to the density of planets in the solar system. So it confirmed that these worlds really were hot Jupiters. They were big, gassy planets, inflated due to their proximity to their stars.
The new-look universe was populating fast, inspiring an eager generation of young scientists to join the hunt.
Timing is everything. When I was in graduate school in the mid-1990s looking for a project to work on for my PhD thesis, amazingly enough, the first reports of planets orbiting sun-like stars were coming around at that time. And my thesis advisor suggested that I work on exoplanets.
MIT professor of astrophysics Sarah Seeger arrived in the field after the paradigm had already shifted. To her, the question was no longer simply, are there exoplanets out there? It was, could there be one like Earth?
When I want to think, I come here to the Great Lake, and I look out on the water, and I just think about how wonderful life is, how fragile life is. It gives me hope that there's another planet out there where life could really thrive.
But what makes our world so special? What physical characteristics define our planet?
We're looking for a planet that has a solid surface, predominantly rocky planet, but we're not expecting another planet to be exactly like Earth. When we talk about the planets we want to find, it's one that would be able to host life.
Even in the most extreme environments, like here amidst the glaciers and volcanoes of Iceland, the conditions that make organic life possible on Earth can be found if you know where to look.
La vie a besoin d'eau. Alors cela dit, de l'eau, on pense qu'il y en a presque partout dans l'univers. Mais essentiellement, en fait, si on regarde sous forme de glace. Et c'est pas ça qu'il faut. La vie telle qu'on peut l'imaginer, chimiquement, et surtout telle qu'on pourra la reconnaître, ce qu'il faut vraiment, c'est de l'eau liquide. Et ça, c'est pas évident, parce qu'il faut les bonnes conditions de température, de pression.
Based on everything we know of life on Earth, scientists like Francois Forget believe that for an exoplanet to host liquid water, like Earth, it needs to lie within a certain distance from its star, a region called the habitable zone.
D'ailleurs, on calcule que si on déplaçait, avec nos modèles, si on déplaçait la Terre de quelques pourcents vers le Soleil, en fait, le climat s'emballerait parce qu'il y aurait un peu plus d'énergie solaire, les océans seraient plus chauds, plus de vapeur d'eau, plus d'effet de serre, et hop, très vite, on peut basculer complètement, les océans peuvent totalement bouillir et s'évaporer. Et inversement, avec la Terre telle qu'on la connaît actuellement, si on la déplace de quelques pourcents vers l'extérieur, on l'éloigne du Soleil, eh bien il va faire plus froid, il y aura plus de neige, plus de glace, et cette neige réfléchit réellement du Soleil, ce qui fait qu'il fait de plus en plus froid, et ça s'emballe inversement, et la Terre peut être complètement couverte de glace, ce qu'on appelle une Terre boule de neige. Ce qui fait que la Terre est particulièrement propice à la vie, c'est pas seulement qu'elle est couverte d'eau liquide, d'océans aujourd'hui, mais surtout qu'elle a été pendant toute son existence, pendant 4 milliards d'années, ce qui a permis à la vie de naître et d'évoluer.
The first mathematical model of planet habitability, produced in 1979, placed extremely narrow limits on the habitable zone. But recent advances in geological science have broadened the horizon.
Other than being at approximately the right distance from the sun, the main thing that keeps Earth habitable is the carbon cycle.
Penn State professor of geoscience Jim Casting is a world leader in the study of planet habitability and the vital role played by carbon. On Earth, carbon in the form of CO2 traps the sun's heat in our atmosphere. Without it, temperatures would plummet to below what life needs to survive. But CO2 doesn't just stay in the atmosphere.
The trees around us are photosynthesizing, and they're actually exchanging every CO2 molecule in the atmosphere every 10 or 12 years. But on long time scales, it's what we call the carbonate-silicate cycle, where CO2 in the combined atmosphere-ocean system is exchanging with carbonate rocks.
CO2-rich sediment washes into the ocean and is drawn into the Earth's crust at underwater fault lines, where a final geological mechanism completes the cycle.
To have a habitable planet like the Earth, you really need a long-term carbon cycle, and that has to be driven by some process like plate tectonics on the Earth that keeps the carbon moving around.
When our planet enters an ice age, this tectonic feedback restores a habitable climate. As oceans freeze, the uptake side of the carbon cycle slows, while volcanic activity continues, pumping CO2 and heat back into the atmosphere.
When you put in the feedback, you find out that the habitable zone, instead of being very narrow, is actually quite wide, and wide enough that there's a good chance that planets around other stars, at least one or more of them, could be within the habitable zone.
Casting's research had a momentous impact. By expanding the boundaries of the habitable zone, the carbon feedback loop vastly improved the odds of finding an Earth-like exoplanet where life might be possible. But the fundamental challenge of identifying an Earth-like planet remained. They're tiny, and therefore much harder to detect, compared to the gas giants that our instruments had observed so far. To see these Earth-sized worlds, a giant leap forward in technology was required.
I was a graduate student when the very first planet was discovered. In fact, I was at the conference where Michel Mayor made that announcement.
NASA astrophysicist Natalie Batala graduated with a dream.
I would say my biggest hope was that we find an Earth-sized planet orbiting a star very much like our own sun, in a similar orbit where the conditions for life might be just right.
Five, 4, 3, 2, engine start, 1, 0, and liftoff of the Delta II rocket with Kepler on a search for planets in some way like our own.
In 2009, scientists launched a formidable new weapon in the hunt for life beyond our solar system. The first dedicated planet-hunting telescope, Kepler. At the time, it was the world's largest digital camera, using an array of 95 megapixel sensors to detect the infinitesimal dimming of starlight caused by transiting planets. So powerful that if turned towards Earth, it could detect a single porch light turning off. More importantly, it was the first instrument capable of detecting rocky, Earth-sized planets.
The first 2 decades of exoplanets was kind of like postage stamp collecting. Kepler really changed that.
Kepler monitored a select region of our galaxy over a 4-year period by taking a snapshot every 30 minutes, like an epic time-lapse photograph.
And from that data, we identified over 4,000 periodic transit events that look like viable planets. And in fact, we have confirmed through other follow-up observations that over half of them are indeed bona fide planets.
Kepler delivered not only the first rocky exoplanets, it revealed brand new kinds of rocky planets, like Kepler 10b, our first encounter with what scientists would christen lava worlds.
These are rocky worlds, same kind of density as Earth, but they're orbiting so close to their star that the surface temperatures are in excess of that required to melt not just rock, but iron. So you've got an entire hemisphere, something the size of the Pacific Ocean, even larger, that is an ocean, but it's not an ocean of water. It's an ocean of molten rock.
Kepler was the first celestial census. Extrapolating the data from the surveyed region, it gave astronomers a catalogue of the exoplanet population.
We've learned, I think, 3 important things. First, we've learned that every star that you see when you look up into the sky at night has at least one planet. The other thing that we have learned is that nature makes small planets more efficiently than large planets. The third thing we've learned has to do with the fraction of stars that harbor Earth-size, potentially habitable planets. And we can make the bias corrections to determine that number. And what we find is that it's about 22 to 25%.
At least one planet for every star in the sky. And as many as a quarter of them Earth-sized and orbiting within the habitable zone. Kepler revolutionized the way we see the stars.
Kepler was the pioneer. Kepler looked for planets transiting sun-like stars. And Kepler looked at a very distant field of stars for 4 years to try to find a planet like Earth that has a 1-year orbit.
Inspired by the success of Kepler, in 2013, NASA joined forces with MIT Lincoln Labs to develop an instrument that could deliver a more detailed survey of nearby Earth-like worlds.
The entire field of exoplanets is funneling towards the search for another Earth, a rocky world orbiting a small star, preferably in the habitable zone of that star.
As the project advanced, MIT professor Sarah Seeger was named Deputy Science Director of the Transiting Exoplanet Survey Satellite, aka TESS.
TESS wants to find stars that are closer, right in our neighborhood, actually. The camera has a lens assembly of 7 lens elements that refracts starlight onto a detector. And together they make a giant strip. When you think of the sky as a sphere, from the bottom of one hemisphere all the way up to the pole. After 1 year of doing that, TESS will flip to the next hemisphere, and it will then do the same thing. And so over 2 years, TESS aims to study the entire sky.
By scanning nearby star systems, TESS aims to identify 50 Earth-sized exoplanet candidates for further investigation. But would finding a planet like our Earth also mean finding a star like our Sun?
All we know of the stars, we know from afar. All we know of Minerva B is this. It is a rocky planet, 1.6 times the size of Earth, hosted by a red dwarf star. Its orbital period is 39 Earth days. It lies within the habitable zone. Its atmosphere contains carbon dioxide, methane, water, and ozone. It will be full of surprises.
After the explosion of discoveries, a new question emerged. Could finding the right star be just as crucial as finding the right planet?
I think the biggest lie that I was told when I was in school was that the sun is an average star. The sun is not an average star. The sun is much bigger, much more luminous, much more massive than most stars. Most stars in the galaxy are about a quarter the size of the sun, a quarter the mass, and they only put out 1/1000th the energy.
These are small, cool stars, burning not yellow like our sun, but red. They're classified as M-type stars, or M dwarfs, but most people call them red dwarfs. One of Kepler's Earth-sized discoveries, planet Kepler 186f, was found to be orbiting such a star, 500 light-years from Earth.
It's about the same size of the Earth. And our observations tell us that planets the size of Earth are more likely to have a rocky composition. So we imagine this planet as being a rocky planet with a surface, a solid surface. It's receiving about the right amount of energy for liquid water to pool on the surface, but it's orbiting a star that's very different than our sun.
Because red dwarfs burn less hot than our sun, their habitable zone tends to be much closer in. But this closeness could spell disaster for life on the planet.
The red dwarfs, their habitable zones are so close in that the planets have a strong chance of becoming tidally locked and synchronously rotating, where they show the same face to the star all the time, just as the moon shows the same face to the Earth. So that poses problems for habitability, which may be difficult to overcome.
When a planet is close to its star, the gravitational or tidal force becomes greater. And this can have the effect of locking the rotation of the planet, meaning one side is always lit by its star, while the other remains shrouded in darkness. As well as producing one hot side and one cold, by spinning so slowly, the planet may fail to generate an electromagnetic shield, which, like on Earth, protects the planet from radiation.
These stars at the same time, they're very much dimmer than the sun, but they're more magnetically active. They give lots of high energy radiation that may strip the atmosphere off a planet, particularly if it's not protected by a magnetic field.
But in 2015, Casting and other researchers found reason to hope for life on a tidally locked planet orbiting a red dwarf. Using sophisticated climate modeling, they proposed that if the planet had the right kind of atmosphere, then heat could be transferred from the light side to the dark, like a reverse cycle air conditioning system. Planet hunters embraced the discovery. If life could thrive on a planet around a red dwarf or M-type star, the odds of finding a second Earth were vastly improved.
M-type stars are the most numerous star in the galaxy. 70% of the stars in our galaxy are these M-type stars. So if life can seed itself and get started on these planets, then life is going to be ubiquitous in the galaxy.
For 4 months at the beginning of 2016, the SEA telescope in Chile set its sights on the M-type star, Proxima Centauri. A mere 4.25 light-years from Earth, it's our nearest stellar neighbor. In a machine room deep beneath the telescope, light from the star was split by the HARPS spectrometer, an instrument so sensitive it picked up the feeblest of wobbles in the dwarf star, caused by a tiny Earth-sized planet, Proxima b. The discovery came as a revelation. The very closest alien star to Earth hosts a tidally locked Earth-like world. And calculations reveal that Proxima b is orbiting within the habitable zone.
It's an amazing triumph to discover a planet around our nearest star. Just think about that. For thousands of years, people have been wondering, are there any planets around other stars? And there is one around our very nearest star.
But what about its atmosphere? Could this planet sustain life?
My last cell of helium-3 propellant is delivered from Moonbase. My preparations are complete. On Earth, the World Astronomical Union is throwing a party for me on the eve of my historic launch. And I am honored. And I am alone. Tomorrow, I am gone to Minerva.
As the exoplanet gold rush gathered pace, planet-hunting prospectors sought ever more refined methods of sifting their discoveries in an effort to give a future interstellar mission the best possible chance of targeting a world that might actually host life. Having identified a rich new vein of distant planets, the next crucial piece of the puzzle was yet to fall into place. How could a telescope be used to sample the atmosphere?
Looking at a planet's atmosphere far away is the best way we have to find signs of life on another world. Because the gases that life produces, here on Earth actually, imprint in our atmosphere in a very significant way. And so it's just amazing to think that on another world we can do the same.
If you were an alien astronomer studying the planets of the solar system, you would see that there's something very different about the third planet from the sun. You would see that its atmosphere is full of oxygen, even though you would know that the oxygen couldn't possibly be there by geologic processes. There would be other gases, like methane, which also shouldn't be present, and yet there they are. And you would, we think, as we're trying to do ourselves, when we look at other stars, conclude that life was the only possible explanation.
In 2000, David Charbonneau took control of the aging Hubble telescope, charged with a single but daunting objective: to make the first ever observation of an exoplanet's atmosphere. The transit method of exoplanet detection, which Charbonneau had pioneered himself, provided a clue for how to solve the puzzle. Planets orbiting closely to their stars make more frequent transits, and the larger the planet, the easier it is to detect. So Charbonneau turned the Hubble's gaze towards Osiris, a gas giant that transits every 3.5 days.
We had the idea that when the planet passed in front of its star, some of the light from the star would pass through the outer parts of the planet, and then imprinted upon that light would be the fingerprints of whatever atoms or molecules were present in the atmosphere.
Different atoms absorb different light frequencies in the electromagnetic spectrum and allow others to pass through, producing a signature in color.
No one had ever discovered an exoplanet atmosphere. And so we needed a guess as to what atom or molecule would be very prominent, would be the easiest first thing to see. So there were some predictions.
Charbonneau put his money on sodium, the telltale yellow glow of street lamps.
The observations were gathered a few months afterwards, and it took more than a year to carefully analyze the data. No one had ever made this detection before, so we wanted to be absolutely certain that what we were seeing was robust.
After painstakingly probing the data, Charbonneau announced his discovery. The atmosphere around Osiris was indeed rich in sodium. However, this was no second Earth. Named after the Egyptian god of the dead, the gas giant Osiris doesn't even have a solid surface to land on, let alone a climate for life.
What we crave to do is to study the atmosphere of an Earth-like planet. Of course, Earth-like planets are simply much smaller than gas giants, and so it's just much more difficult to detect them and to study their atmospheres.
It's the hurdle that has thwarted planet hunters from the outset. The blinding light of the stars completely overwhelms the smaller exoplanets. The first instrument to solve that problem will hold the key to the exoplanet revolution.
Donc ce télescope va nous permettre de faire un bond en avant dans plusieurs domaines de l'astrophysique, et notamment le domaine des exoplanètes. En effet, il va nous permettre d'aller voir l'atmosphère de ces exoplanètes.
The James Webb Space Telescope is designed to view the heavens like they've never been seen before, making the invisible visible. Its vast honeycomb-like dish of mirrors converges light into the eye of a state-of-the-art infrared camera that astrophysicist Pierre-Olivier Lagage spent 20 years developing.
Un objet, selon sa température, émet dans une longueur d'onde donnée. Par exemple, le Soleil émet dans le domaine visible parce qu'il est très chaud. Si on prend un humain, il est beaucoup plus froid et il va émettre dans une autre longueur d'onde, l'infrarouge moyen, et c'est pour ça qu'avec une caméra dite thermique ou d'infrarouge moyen, on peut voir les personnes la nuit. On n'a pas besoin de lumière, on voit la chaleur émise par un humain, par exemple, dans l'infrarouge moyen.
The same is true of exoplanets. Observe them in the right wavelength, and they glow in the dark. But for the infrared vision to work, It relies on the truly innovative feature of this telescope. Inside the camera lies James Webb's secret weapon, a kind of mask called a coronagraph.
Mais tu vois, cette forme de masque est très particulière et la lumière de l'étoile arrive là où c'est opaque. Par contre, si tu as un petit objet à côté, une exoplanète par exemple, eh bien la lumière va pas avoir exactement le même chemin et va passer dans les trous. Donc après, on va pouvoir avoir la lumière de l'exoplanète sans avoir la lumière de l'étoile. Alors, grâce à ce mode coronographique, on va pouvoir aller voir les exoplanètes en imagerie directe.
The mask of the coronagraph intervenes between the overwhelming light of the star, like an eclipse, allowing the infrared light of the planet to shine through.
On n'a jamais regardé ces exoplanètes dans ce domaine de longueur d'onde, et pourtant c'est un domaine très intéressant pour mesurer la température de ces objets, leur luminosité. On peut aussi voir la composition. Il y a certaines molécules, comme l'ammoniac, qui est dans ce domaine de longueur d'onde. Donc la caractérisation des atmosphères sera un des grands sujets avec cet instrument.
Crucial in the hunt for Earth-like worlds, James Webb is ideally suited for detecting ozone.
Pourquoi de l'ozone? Parce que l'ozone, naturellement, sans vie, sans oxygène, on pense qu'il n'y en a pas. Donc on pense que c'est vraiment quelque chose qui est une trace de vie. Et dans le domaine de l'infrarouge moyen de notre instrument, on a justement cette signature d'ozone.
The James Webb promises to be the missing piece in the planet hunter's arsenal. With its breakthrough ability to view an Earth-like exoplanet directly and to study its atmosphere, the odds of identifying a destination for a future landing mission have never been better.
You know, I can probably imagine what that would feel like better than most people can. I've been sending robotic missions to other planets my whole career, 40 years of this. But I can't imagine what it would feel like. I mean, the problem of getting a spacecraft with that kind of capability to another star is so much harder.
The discoveries of the planet hunters transformed the way we see the universe and posed to explorers like Steve Squires, lead investigator of the Mars rover missions, the next tantalizing question. What if we could reach out to a nearby alien star and search for life on a second Earth? What if we could land on another rocky world with running water and a protective Earth-like atmosphere?
If you could find an Earth-like world that has been around for billions of years, enough time to develop advanced biology, it's had the right conditions all that time, there are all kinds of possibilities. I can't imagine what it would feel like. It's going to be, I mean, it's going to be a shared moment for all of humanity when it happens.
Five, 4, 3, 2, 1, I launch. No fireworks, no trembling earth. For those of you who are watching this, I thank you for entrusting me with the greatest adventure in human history. Wish me luck. My name is Artemis. My time has come. I initiate launch sequence and maneuver for exit trajectory. My navigation systems target Mars' sphere of influence for gravity assist and angular trim towards Jupiter. I am ready to escape Earth orbit. Total distance, 4.7 light years. I commence acceleration phase for maximum velocity, 51,000 kilometers per second. It will take me 49.8 years to reach my destination. The Earth-like exoplanet Minerva B. My mission is simple. Find life.
It was only for graduate students, and I was an undergraduate, and I nearly got thrown out of the class the first day. And got to be, I don't know, 3-4 weeks in the semester, I'm thinking, I better start thinking about my term paper. And there was this place then, at the time, called the Mars Room, and it was a place where the pictures from Mars were stored. And I went in, and I thought I'll sit down for 15 or 20 minutes and flip through some pictures and see if I can come up with an idea for a term paper.
Like most scientists, principal investigator of the Mars rover missions, Steve Squires, is a born explorer, a seeker of truth amidst the great unknown.
I mean, ever since I was a kid, I've been fascinated by maps. I was fascinated by, remote corners of Tibet, or the deep ocean, or the other side of the moon. Just the idea that there was a place that we hadn't seen yet, and then being able to go there and see it for the first time, that just had a huge appeal for me.
In 1977, images of the Viking mission changed the course of Squires' life.
It's not like today where pictures come down from Mars and bang, they're on the internet an hour later. There were only a few dozen people in the world who'd seen these. I didn't understand what I was looking at in the pictures. Nobody did. But then I would see in the pictures these little valleys that just looked like they had to have been carved by liquid water. And I was in that room for 4 hours, and I walked out of there knowing exactly what I wanted to do with the rest of my life.
At this point in time, we should be on the ground.
In the early 2000s, Squires led NASA's Spirit and Opportunity rover missions to Mars, successfully landing the 2 robot geologists in a bid to uncover the hidden history of water on the Red Planet. Amid these groundbreaking triumphs, an even greater frontier beckons. The discovery of Earth-like worlds outside our solar system has transformed the way we see the universe and presents an irresistible challenge. Why not reach out even further and search for life on a planet among the stars?
The thing that has driven the focus of exploration in this solar system has been the search for other forms of life. And so I think the motivation is going to be the same thing. I think the motivation when you go to other star systems is going to be habitable worlds and possibly worlds with life. That's the thing that's going to draw you to a specific world.
But the scale of the challenge is unlike anything humankind has attempted before. The closest star that hosts an Earth-sized planet, Proxima Centauri, is 4.3 light-years away, over 170,000 times further than Mars. The quest to build a spacecraft that can journey to the stars will test the greatest explorers of our generation and demand of them the ultimate sacrifice: to give all their craft and vision for a dream they'll never realize.
You're asking people to devote their careers, their lives, to something they will never see to fruition. Now that has happened. That has happened a few times in human history. Some of the great cathedrals of Europe took longer than a human lifespan to build. People felt guided by a higher power when they did that. But it takes something extraordinary to motivate people to do that kind of thing.
I enter the shadow of Mars. The lights of Viking colony winking. A final farewell from humankind. My transceiver dish receives their message. Bon voyage. I fly by the storm of Jupiter, onward to Pluto and Chiron, and into the space between stars. After 3 months of acceleration, my speed is 19 kilometers per second. I meet Voyager 1, 170 years and 72 billion kilometers from Earth. No fuel to shift course. No power to call home. I have now traveled further than any spacecraft before me. I retract my transceiver. There will be no more calls. And press on through the silence to Minerva.
I get up each day with joy. You know why? Because I know that day I'm going to learn something I didn't know before, and that my picture, my overall tapestry of who we are, who I am, what our species is, and how we got to be that way will be lifted up.
NASA's chief engineer of planetary flight systems, Gentry Lee, is a pioneer of exploration. At the age of 75, he's dedicated over 50 years of his life to engineering robotic missions to other planets.
Someone asked me one time if I had to describe the excursions above the threshold of joy in my life, would there be a lot of them or just a few? And I said, I can give you the two categories right away. The birth of my children, and I now have 8, and when a spacecraft that I had a major role in achieved something successfully. And there's also been 8 of those.
Lee's first mission, Viking, in 1975 was humanity's opening shot in our dream of exploring the solar system. Designed to achieve what many thought impossible, to make the first ever landing on another planet, Mars.
We had lived through 5 years of people telling, it's not going to work, you don't have everything under control. And we were scared to death that it wouldn't work.
ACS is close to vertical. Have a screen for touchdown confirmed. Fantastic. 16 kilometers.
And the moment that first strip of picture came down from planet Mars on July the 20th of 1976, there were hundreds of us who immediately, spontaneously, tears burst from our eyes. It was at that moment that we knew that human beings, who had always been a Category 1 species, limited to their own Earth and its sphere of influence, had reached out and become a Category 2 species, ready to explore the entire solar system.
Over the next 5 decades, Lee oversaw successful missions to Jupiter, Pluto, and to the comet Tempel-1. With Lee and other pioneers at the helm, humanity's exploration of the solar system has been so successful, we have a permanent office in space, the International Space Station. But as the new dawn of interstellar exploration lights the horizon, even the old sea dogs know it will be the greatest challenge that humankind has ever faced.
It is hubris on our part to imagine that we can sit today and define all the steps that lead us to this plethora of technology advances that we need in the future to build an interstellar spacecraft. Rather, let us do the following thing. That spacecraft must communicate, it must navigate, it must have propulsion, it must have the ability to take data. It's as if Henry the Navigator, as the King of Portugal, had said, I don't even know yet what kind of ships I need to build or where they need to go. Let me just start with an idea. What floats?
And so the infinitely complex quest to search for life amongst the stars is reduced to just 4 problems. Propulsion, navigation, communication, intelligence. Each one of them will demand a revolution.
I am 9 years into my journey, 1.2 light years from Earth. 26% of my acceleration phase complete. My speed is 13,000 kilometers per second. My fuel usage, 19%. I jettison my spent fuel cells. I am on course for arrival at Minerva in 31 years' time. Does life await me?
When I was about 10 years old, I had one of these department store telescopes, learned how to use it, took it out one night, and focused it on what I was told was the planet Saturn. And when I lined up the viewfinder and held it still, and I could see Saturn and its rings, at that moment, I felt a calling, and that calling was to learn about how to get there.
T-minus 10, 9, 8, 7, 6, 5.
Les Johnson answered that calling. becoming a world-leading expert in advanced concepts at NASA Marshall Space Flight Center. In 1999, he led pioneering research into interstellar propulsion.
Nature is kind to us in the regard to what options we're going to have to get to the stars. Nature has said, you smart people, you can figure this out. It's just going to be really hard. It was difficult enough to go to the moon. We're sending probes to the different planets in the solar system. But to take that leap to go to the stars, the distance is just so much further and requires so much more energy that it's just going to take some time.
The goal of engineering missions to the stars confronts explorers with distances they've never even contemplated before. 1 light year is over 9.4 trillion kilometers, which makes our nearest star over 40 trillion kilometers away. That's more than 1 billion round-the-world flights. According to the masters of solar system exploration, the greatest challenge is how to propel a spacecraft fast enough to travel light years within a lifetime.
In order to get humans to make the enormous effort required to fly that kind of mission, you need to have the period of time between when you launch and when you actually get information back be no longer than a typical human lifespan. Humanity has never launched multi-generational voyages of exploration. It's simply never been done.
The distances are just daunting. And so there's going to have to be major breakthroughs, mostly in propulsion.
Chemical-fueled rockets like Saturn V have been the workhorses of solar system exploration. They got us to the moon in just 3 days. But to reach a planet orbiting our nearest star within a generation, we'd need to travel at a speed that covers the Earth-to-moon distance in just 8 seconds. That's 17% the speed of light.
Chemical rockets are great for getting out of the gravity well. You have the high thrust to overcome Earth's gravity, but they're terribly inefficient. And in order to get to the stars in a reasonable amount of time, you're going to need to get up to some pretty high speeds. And it's not just the thrust, it's how efficiently you do that. Because if you're inefficient, you have to have a lot more fuel and you get to a point where you can't carry enough fuel to move your own weight.
The capability of any propulsion system is governed by the rocket equation, a trade-off between thrust, efficiency, and weight. The most powerful chemical rocket in operation, Falcon Heavy, first launched in 2018, weighed 1.5 million kilograms at takeoff, and 95% of it was fuel. It burned through all that fuel in just 10 minutes in order to create enough thrust to deliver its unusual payload beyond Earth's gravity. Wherever Starman is going in his Tesla, it isn't the stars. Only one chemical-powered spacecraft has ever made the leap beyond our solar system. In 2013, 36 years after its launch, Voyager 1 entered interstellar space at 17 kilometers per second. Fast enough to travel London to Beijing in under 10 minutes. But at less than 0.0001% the speed of light, still painfully slow if you're aiming for the stars.
They're well beyond what's considered to be the physical boundary of the solar system. And it's taken over 30-some years to get there. At that speed, they'll take 70,000 years just to get to the nearest star. Now, chemical rockets aren't going to do it.
As the push for interstellar exploration gathers pace, the workhorses of the old space race are put out to pasture. Monuments to a bygone era. But if not chemical rockets, what will deliver the seemingly impossible thrust and fuel efficiency required to journey to the stars within a lifetime? 3 potential propulsion solutions are being explored today: fusion, antimatter, and plasma.
Alors imaginons qu'on veuille aller vers Proxima du Centaure, donc l'étoile la plus proche de notre système solaire, à 4,3 années-lumière. Et imaginons qu'on veuille y aller en quelques décennies. Si on veut utiliser un moteur de fusée classique, en fait, on peut montrer que la quantité de carburant qu'il nous faut, elle est supérieure à toute la masse de l'univers connu. Par contre, si on utilise un propulseur à plasma, eh bien, en fait, il nous faudrait simplement quelques dizaines ou centaines de kilogrammes de carburant. Donc là, la mission devient possible.
Physicist Stefan Mazouf is working at the cutting edge of electric propulsion. The Hall Plasma Thruster.
On part d'un carburant, plutôt sous forme gazeuse, on va l'électriser, et ces particules électriques, qu'on appelle des ions, vont être éjectées à très grande vitesse. C'est l'éjection de cette matière qui va faire avancer le véhicule spatial.
On va rentrer le moteur.
Ok, très bien.
Since the 1970s, plasma thrusters have been used in satellites to make positioning adjustments while in orbit.
So he's coming up on 90 meters and closing. Range is 70 meters and range rate 0.34.
Their principal advantage is efficiency, demanding just a tiny fraction of the mass of fuel required by chemical rockets.
Prenons l'exemple de la sonde Voyager 1, qui se déplace actuellement à 61 000 km/h. Avec un propulseur chimique classique, un moteur de fusée, on peut atteindre cette vitesse en quelques jours, et en consommant 92 tonnes de carburant. Un propulseur à plasma utilisé aujourd'hui sur satellite permettrait d'atteindre cette vitesse, certes en 2 ans, mais en consommant uniquement une dizaine de kilogrammes de carburant. Cependant, si on embarque beaucoup plus de carburant, on pourra utiliser le propulseur pendant beaucoup plus de temps, et donc au final atteindre une vitesse très supérieure à celle de la sonde Voyager 1, voire même atteindre une fraction de la vitesse de la lumière.
Plasma engines offer hope of achieving the speed required to reach the stars. Still holding them back is how long it would take to achieve that speed, dragging the total trip time into thousands of years. But in the shimmering upper atmosphere of our own planet lies the potential for a kind of propulsion until now only dreamt of in the realm of science fiction.
I am the navigator. My mind is full of stars, and every planet and every moon. Every celestial body that is known, I know also. But the dangers my creators did not know of, I must discover for myself. an asteroid field. I turn to face it, head on. My titanium shield absorbs the impacts. But one stray penetrates my mind. My emergency backup command system activates. I am reborn. I re-engage. I journey on.
In 1995, at the CERN Particle Collider in Switzerland, for the first time in human history, scientists succeeded in producing the most efficient source of energy achievable within the laws of physics: antimatter.
As any good Star Trek fan will know, right, on the Enterprise, that's what powered their warp drive. Of course, warp drive is science fiction drive. But if you think about antimatter, it's real. Just like normal matter is protons, electrons, there are antiprotons and anti-electrons. When matter and antimatter come in contact with each other, they annihilate. And it essentially is the perfect E equal mc squared moment as released as energy. And therefore, it's the most efficient battery we can ever build, most efficient battery that nature will allow us to have.
Antimatter is created naturally in space when cosmic rays collide with atoms in the Earth's atmosphere. Producing it at the CERN was a phenomenal scientific and engineering breakthrough that required accelerating particles to the speed of light and smashing them together. The challenge now is how to create enough of it to propel a spacecraft.
This is where it gets tough. If you look at the total amount of antimatter produced globally today, it's on the order of nanograms. You would need on the order of kilograms, perhaps up to a ton of antimatter to drive a starship. That's not something I want to do on the Earth, because the amount of energy released if that ton of antimatter met a ton of matter would be catastrophic. And so you're going to have to build the ability to, you have to make your antimatter in space, far away from the Earth, and use that for your starship construction. So again, it's not practical today, but it's not impossible.
The stars themselves suggest another possible solution to the propulsion problem. The energy released from hydrogen atoms fused together is what lights the sky across the universe. Since the 1950s, scientists have been developing fusion reactors to harness it.
The sun does it by brute force, has all that mass, squeezes all that hydrogen together to form helium, releases energy, and that's how the sun shines.
It's the holy grail of energy production. Tame the power of the sun and furnish humanity with an infinite supply of energy. But to get fusion going on Earth, you need to generate the heat of the sun. Upwards of 100 million degrees centigrade.
Well, we've achieved fusion on the ground. It's been done. Fusion happens when a hydrogen bomb is detonated, which is not what we want.
In the hydrogen bombs of the mid-20th century, the atomic explosion of a radioactive isotope was used to produce the heat required to achieve fusion. But that explosion of energy was not contained in a way that it could be harnessed.
What you want to do is be able to capture the energy source of the sun in order to heat your propellant or to use as propellant to get your spacecraft going fast enough to go to the stars.
Modern reactors achieve fusion by other means, by heating plasma. The problem with this approach so far is that the energy required to reach that heat has been greater than the energy produced by fusion. No reactor on Earth yet has even reached break-even. But at Princeton Satellite Systems, a team of engineers is on a mission to solve that problem and to build a fusion reactor that can take us to the stars.
My brother will tell the story that I'm the only person he knows that's actually doing what they thought they wanted to do in high school. I identified aerospace engineering. I picked colleges for aerospace engineering. I've been doing aerospace engineering ever since because it's really fun and challenging. Space is cool. The exhaust velocity that we have is only about 100 kilometers per second. And yet you can't get there fast unless you got some meaningful thrust.
Right, so you would...
Aerospace engineer Stephanie Thomas is principal investigator in a NASA-funded program to build the world's first direct fusion drive,
Essentially, it's a straight line.
an integrated reactor and propulsion system in one.
We want to reach a neighboring star in the neighborhood of 5 light years distance. We want to bring 10,000 kilograms of payload, that's 10 metric tons, and we need to do it with an exhaust velocity that we can actually achieve with an engine.
Thomas's first challenge is to achieve a constant flow of plasma to catalyze the reactor.
We're getting pulses, so we're pulsing current through these antennae. So every time we're running a 5 millisecond pulse, we heat the plasma, we generate current, you see a flash. But the reactor would be steady state. So instead of flashing like this, it would be bright all the time. So that's the goal.
Rather than using a heavy and hazardous fuel like uranium, the direct fusion drive runs on a naturally occurring isotope of hydrogen, deuterium, found all over the Earth in water. The drive unit is compact, at just 1 meter diameter and 10 meters long, small enough to mount on a spacecraft.
We think that we can build the next generation machine in maybe 5 years. It will take at least another 5 years to build a prototype that you could launch. But definitely 15 years at the outside, we think we could have one and put it in space. At some point, we have to visit the stars. We're never going to just sit here and be content, you know, even when we're visiting the planets, because we want to know what's out there. Everybody wants to go to the stars someday.
In the timeline of propulsion technology, that someday is getting closer. The next challenge in our bid for the stars is navigation.
I discard my primary engine, 15 years out from my destination. At 51,000 kilometers per second, my acceleration phase is now complete. I deploy anterior thrusters and engage reverse propulsion. I set deceleration at minus 168 kilometers per second squared. Total ship weight now 42,000 tons and decreasing 75 kilograms per second of propellant burnt. I refined my trajectory and set course for Minerva.
In the realm of space exploration, the solar system is our neighborhood. Since visiting the moon in '69, we've dropped in on almost every body around the sun. In 2015, the New Horizons probe completed the first flyby of our most distant neighbor, Pluto. It took over 9 years to get there, but at every step of the way, the unmanned spacecraft was guided remotely from Earth.
The way we navigate today, when we send these probes out, even the one that went to Pluto, is we have a combination of data taken by the flying spacecraft and our big computers here on the Earth that are processing radio information that comes from those spacecraft. When we went by Pluto, we were basically so accurate that we were hitting a golf ball into a hole from Los Angeles to London. That's how accurate that was done.
Sending directions to probes works for solar system exploration. But as we set our sights on the stars, the distances are so enormous, a new question emerges. How to navigate a journey of light years?
If we were ever to go explore a planet around another star, the distance would be so great that the machine would have to essentially operate on its own. We call that autonomy. We're taking big steps in that direction. With Curiosity, we did a lot.
Landed on Mars in 2012, Curiosity was the first spacecraft equipped with an autonomous navigation system. Given coordinates by mission control, the rover could image its surroundings and compute a safe path across the Martian landscape. But for an interstellar mission, there will be no relaying instructions.
All the navigation would have to be on board. All the algorithms, the computations of the orbit, the computations of the maneuvers to get to the right place, what stars to look at is for this year, what stars to look at for next year. What we would have to do is extend our minds to imagine all the possibilities that they might run into. And we would spend literally years building this hierarchy of possibilities into this artificial intelligent machine. It would have to know at all times how well all its critical systems were doing and how to fix them if they weren't working right and how to replace them if they couldn't be fixed. What a challenge.
I enter the Minervan star system, 49.6 years since my departure. I reopen my transceiver and prepare to send the message home. I have arrived.
With any mission, communication is paramount. Most spacecraft do not return. Instead, they send their data back to Earth.
When great distances in the speed of light
get involved, it becomes a very, very different sort of experience. Simple words like now take on a kind of a different meaning. I remember when we were landing on Mars, from when you hit the top of the Martian atmosphere to when you're on the surface takes about 6 minutes. At that time, what we call the one-way light time, how long it takes a signal to travel at the speed of light from Mars to Earth, was 10 minutes.
All systems are go. We are currently 6 minutes away from hitting the top of the Martian atmosphere.
So we're sitting there in the control room, and we're watching the radio signal, and we're watching the spacecraft begins to slow down and curve down in the Martian atmosphere, and it's just at the top of the atmosphere. The reality is, out at Mars, it's been on the surface for 4 minutes.
Moving at a speed of 173 miles per hour, we are here.
And it may be a happy, healthy rover, or it may be a smoking hole in the ground, and I don't know. But I'm watching this, and I'm not seeing reality at that moment. And magnify that. So instead of 10 minutes, it's 10 years.
Communication with every craft currently in space is conducted via the giant dishes of the Deep Space Network, each powerful enough to track a signal from Pluto, no stronger than a CB radio.
All of our deep space communications are run through the Deep Space Network. That's an array of very large satellite dishes. They're set up at 3 locations around the world. One is in California at Goldstone, one is in Australia at Canberra, and one is in Spain at Madrid. We need a very large dish area in order to collect all the energy and be able to communicate all the way out at places like Pluto, where our spacecraft are going.
In 2014, Matthew Abramson was mission manager of a radical new form of communication installed on the International Space Station, designed to overcome the limitation of traditional radio transmission.
The limitation is primarily the distance that we're sending the transmission over. When we send out that signal, it spreads out over time and over space. And so as that spreads out, it dilutes the signal power. The further out you go, the lower and lower your data rate is, or it gets out to the level of something like your dial-up modems that we used to have many years ago.
When the New Horizons probe sent back pictures from Pluto via radio transmission, the signal was so weak, it took 15 months to downlink the images from a 12-hour flyby. But with the technology Abramson launched and tested in 2014, that download time could be reduced to just 1 day by sending data back to Earth on beams of light.
The idea is you take a focused laser beam and send the signal, same signal over that beam, but it's much more efficient because you have this focused signal that's not spreading out as much over time.
Laser wavelengths are packed much more densely than sound waves, so they transmit more information per second and with a stronger signal. The greater bandwidth allows spacecraft to downlink multiple large packets of data simultaneously and in record time.
The reason for that is as we go further out into the universe and we go to places like Mars and Jupiter, currently today we're just getting back single images of the science. And in the future, if you do have a high bandwidth system like an optical system, you could get back high definition video. And I think getting high definition video back would be a game changer for space exploration.
I fly by the gas giant's exoplanet, Minerva C. I use its atmosphere to create drag and pull me in towards my target. I trace an elliptical trajectory around the Minervan sun and emerge to take my first glimpse of my new home. I decouple from my antenna. My Explorer module holds my mind. I commence entry, landing, and descent sequence. I enter orbit. So close now. I deploy my satellites to map the surface and scout potential landing sites. Is this new world ready to be known?
The part of this that is thrilling to me is that our best attributes, if done correctly, exploration at its finest, have been programmed into an extension of our species. It belongs to no single individual. It is, more than anything else, a symbol of humanity working together to create something whose only purpose is to gather knowledge. What a beautiful thought. And after a long period of time, finally the moment of truth is coming. And more than likely, the people that designed it originally are no longer alive.
Welcome to the ops lab, Francesca.
And they have passed on this thrill, this passion to their children and perhaps even to their grandchildren.
Okay.
We're going to walk around on Mars, Francesca.
This one's cool over here.
Uh-huh. Will it be that they found life? Will it be that they found a planet where we could someday exist? Whatever it is, it will be a historical milestone unlike any other.
That moment when something new is revealed that no one's ever seen before, that's just glorious. That's exploration. And it's going to happen when we go to other worlds around other stars in a very, very, very big way. We'll be sitting back on Earth, and that downlink will come, and the video or the pictures or the spectra or whatever it is are going to come up on the screen, and everybody's jaws are just going to drop.
This could be the end. I release my landing capsule into the unknown. If I touch down, if I am welcome, if I find life, this could be the beginning. I am Artemis. I am the mind of the mothership. I am the body that has traveled where human bodies cannot go. To an alien world, 4.7 light years from Earth. On a mission to solve the mystery. Is there life beyond our solar system? I release my landing module into the atmosphere of the exoplanet Minerva B. Two centuries of human labor and human hope have brought me to this moment. And I am ready to touch down. I am ready to explore. I am ready to discover life.
Four and a half billion years ago, in the nursery of the heavens, a star was born. A giant cloud of dust and gas distended and ballooned until under the burden of its gravity, it collapsed upon itself, swirled into a disk, and forged a solar system from the dust. That star was our sun. Of the planets that were formed, only one that we know of gave rise to life. But could our sun, our solar system, our living Earth, have produced the only Genesis among the stars?
My intuition is that the universe is full of life. There's no reason fundamentally it might not look like Earth, with vegetation and animals. Well, the question that I'm interested in is really the start of life. And on Earth, we see for a long time life was just microbial, but all the essential features of life were there. Nothing new was invented when life became trees and animals. That was just morphological. That's just window dressing. To me, it's actually not very interesting at all. Everything interesting with respect to biology was present when there were no trees and no animals and life was just microscopic. The DNA was there, the amino acids was there. All the biochemical machinery that makes life life was there.
Life is a miracle and an enigma, even to those who've spent their own lives trying to crack the code. NASA planetary scientist Chris McKay is one of them, part of a generation of scientists on a quest to find a second Genesis beyond Earth.
The search for life began with a lot of optimism, focused on Mars. Here was a planet that could have had a thick atmosphere and could have had water in the recent past, and in the popular literature at least, still had water. So the search for life on Mars really was thought to be easy.
In 1976, NASA's Viking mission made the first ever landing on the Martian surface. looking for the life that had been hoped for.
Well, turned out a lot harder. Nature was guarding her secrets much more closely than we imagined. So then things basically went quiet in the search for life. And I think they were sparked again, not on Mars, but in the outer solar system.
3, 2, 1, and liftoff of the Cassini spacecraft on a billion-mile trek to Saturn.
In the final decades of the 20th century, humanity launched a series of ambitious missions to explore the outer solar system.
Standing by for solid rocket boosters. All systems go at this time.
The discovery of liquid water on the moons of Jupiter and Saturn, in the misty plumes of Enceladus, and the subterranean oceans of Europa and Ganymede, has opened a thrilling new chapter in the search for a second Genesis. The impact of identifying a separate origin of life on one of these worlds would extend far beyond our solar system.
Finding life that's distinctly different, that truly represents a second genesis of life, well, that would tell us that the answer's not one, it's two in terms of life in the universe. And going from 1 to 2 is huge, because on the scale of the universe, the only numbers that make sense are 0, 1, and infinity. And what we learn in our solar system will then guide how we search for life beyond.
The renewed optimism in the search for life within our solar system emerged alongside a discovery that transformed the way we see the universe. In the early 2000s, NASA's Kepler telescope revealed that every star in the galaxy, just like our sun, is orbited by at least one planet. And up to a quarter of these so-called exoplanets are believed to be suitable for life. In the Milky Way alone, that means roughly 400 billion solar systems and 80 billion potentially habitable worlds. The odds of finding a second Genesis have never been better.
The way I like to think of this is that life will arise anywhere where the conditions are right. And the trick in that is what constitutes the right conditions.
Planetary scientist Jonathan Lenine is another veteran in the hunt for life beyond Earth. But what exactly is life? And how does one search for it?
The basic essentials for life to begin and to exist are liquid water, organic molecules, because carbon is really the essential versatile element that can combine with other elements in many different ways to make the structures of life. Free energy, and minerals and nitrogen to provide the other elements that are required to keep the chemistry going, to generate catalysts that generate more catalysts and more structures until we get to the complexity of a primitive cell.
Liquid water, carbon molecules, energy, minerals, and the secret formula that animates it all into a living cell. These ingredients, this recipe for life, is what our scientists are hunting for on other worlds.
I deploy my spider bots onto the Minervan surface. I 3D print a fleet of drones, and I let them fly. With these eyes and these instruments, I will taste and touch and see this new world for the first time. Will I find all that is hopeful?
Exoplanets are the new frontier in the search for life beyond Earth. But the prospect of exploring distant worlds presents an expanding universe of rivers to cross and mountains to climb. How on Earth can we prepare to explore planets we know so little about?
Exoplanets present a real challenge because there's so much uncertainty. So knowing whether or not you're going to find a cliff face versus a desert versus an ocean versus an ice tundra, we may not know when we launch. So you've got to design your system to survive and operate in all of those possible conditions.
At NASA's robotics headquarters in Pasadena, California, around 100 young engineers are busy reinventing the wheels of the rovers of old.
With planetary exploration, we started with a large robot that was very stable, very safe, and now we're beginning to take more risk. We're trying to get to new places, trying to shrink down the size of the platform, do more with less.
It's a pretty perfect ledge over there.
Yeah. It's the sort of thing other rovers can't fit into.
Some of our robots are designed to climb up different surfaces. So we have a claw-inspired robot that uses sharp hooks to grab onto the rough surface, kind of like an insect or a rock climber would scale up a cliff. We also use electrostatics to stick to surfaces. So this is like rubbing the balloon on your head and it sticks to the wall.
One of the key innovations in the new breed of robotics is biomimicry, using biological systems and processes as the model for design. To look for life, behave like life.
We have created a material that has mechanical properties similar to that you see in biological tissues. We have already, with this system, developed swimming robots.
There is a lot of work today in robots that can go between dry surfaces and water-like surfaces. Wherever we find water on Earth, we find life. So we have a strategy that we've used on Mars called Follow the Water. I think we're going to use that same strategy when we visit an exoplanet.
I follow the alluvial plain of a retreating glacier. My hygrometers detect increasing humidity. I am on the scent of fresh water, tracing its inevitable course, its branching channels over wide floodplains, consuming rock and mineral, now growing brackish, perhaps estuarine. Fresh water and sediment meeting the insistent flow of an incoming tide. there is a river-ocean system on Minerva B. An ideal breeding ground for life.
This is a place where there's life, but it's not life as we're familiar with it. Here, life is pink and living in saturated salt. It's not the kind of green things we normally think of as life.
The salt ponds of San Francisco Bay are a naturally occurring wetland, reshaped by human industry and colonized by trillions of colored microorganisms.
These are a type of halophilic archaea. It's a particularly unusual type of microorganism. It's extremophile, it requires high salt, and it lives in an environment where only it can survive, so it dominates. So where it grows well, and it's the king.
What these salty bugs have in common with everything from oak trees to humans is access to liquid water.
All life on Earth, in some sense, is fragile. It's all tied to the availability and the chemistry of water. We tend to think, well, life on Earth is expanded to all the corners of the Earth, and it's everywhere. That's because water is everywhere on this planet. This is a water planet. But when we look beyond the Earth, we realize that water is in fact rare. The liquid state of water is rare, and life is not the all-conquering capability. Life only can squeeze itself into those environments where there's liquid water.
Water's interesting in that if we look at carbon, which is the next part of the recipe for life, where water is liquid, carbon can be a solid, a dissolved ion, or a gas, all coexisting in the same place. Carbon is an unusual element in that it is capable of making many, many different kinds of molecules. There are literally millions of organic molecules known. And water then becomes the milieu in which all of the chemistry of carbon that leads to us is going to take place.
Carbon-based organic molecules, like amino acids, are the building blocks of life, combining in liquid water to form the structures of every living cell. On Earth today, these complex molecules are everywhere. But where did they come from?
Sur Terre, le problème qu'on a un petit peu dans le scénario de l'apparition de la vie, c'est que la Terre s'est formée environ il y a 4,5 milliards d'années, qu'elle a eu une période assez tumultueuse dans sa prime enfance avec des bombardements météoritiques très intenses. Ça a été un environnement extrêmement chaud qui n'est pas nécessairement propice à l'apparition de molécules complexes. Des idées ont commencé à germer à ce sujet. Est-ce qu'une partie de cette matière organique peut venir de l'espace?
In March 2004, the European Space Agency launched the Rosetta spacecraft on a hunt for the building blocks of life beyond Earth. Its destination was 400 million kilometers away and counting. A moving target hurtling through space at 60,000 kilometers per hour. A lump of ice and dust the size of Mount Fuji. The comet, 67P. Rosetta's mission was to land on it and find out what it's made of. From 2011 onwards, Nicola Altobelli was Rosetta project scientist.
On a dit que les comètes, quand elles se sont formées, sont restées un petit peu dans un état figé, qui n'a pas été modifiée depuis des milliards d'années. Donc peut-être l'idée, c'était qu'elles ont incorporé le matériel organique qui était déjà présent dans le nuage moléculaire à partir duquel le système solaire a évolué.
Because comets formed in the icy outer regions, they hold a frozen record of the solar system's birth. And as the young Earth cooled and oceans formed around 4 billion years ago, some of those same comets came crashing down to Earth. So could it have been comets bearing the carbon-based organic molecules from our solar system's birth that seeded life on Earth? It was the task of Rosetta's landing module, Philae, to find out.
Le moment de l'atterrissage a été un moment aussi émotionnellement très fort. Il s'est déroulé sur une journée complète. C'était le 12 novembre 2014. Le matin, il y a eu la confirmation de la séparation. Premières images sont arrivées, prises par le lander au moment où il se séparait de Rosetta. Ensuite, il y a eu 7 heures d'attente.
Around 4 p.m. came the confirmation of touchdown. But the follow-up signals suggested something wasn't right.
Les premières images panoramiques qui devaient être prises de la surface indiquaient aussi une orientation de l'atterrisseur qui n'aurait pas dû être telle qu'elle était. Donc c'est au fur et à mesure ensuite des heures qui ont passé qu'on a compris que l'ancrage n'avait pas réussi.
Philae had bounced back into space, then bounced a second time before finally coming to rest several hundred meters away.
Je me rappelle d'ailleurs quelqu'un qui disait Philae danse un peu la samba. Mais on a récupéré la plupart des expériences scientifiques qui étaient prévues. On peut même dire que ce rebond sur la comète en plusieurs endroits, ça a permis d'obtenir des données de différents endroits de la comète. Et l'orbiteur, lui, a parfaitement rempli sa mission.
The results were remarkable. Philae detected 16 organic molecules in just a tiny sample of dust kicked up by the initial touchdown. Among them, some of the key building blocks of life on Earth.
50% en masse des grains de poussière éjectés par la comète sont de la matière carbonée organique. Ce matériel organique provenait très vraisemblablement du nuage moléculaire à partir duquel le système solaire s'est formé. Les découvertes de Rosetta nous enseignent que les molécules organiques nécessaires à l'apparition de la vie sur Terre étaient déjà présentes dans l'espace.
Rosetta demonstrated that the building blocks of life on Earth were created during the birth of our solar system. But what about beyond? Could these same vital ingredients be part of the birth of all stars?
Looking back at our own Earth and why we have this rich, biosphere, well, we think it all started with having all this organic material that we are made up of, that was delivered from space, from comets and from asteroids. So we were thinking about the likelihood of life elsewhere. We're pretty much thinking about the likelihood of having that same scenario taking place.
In 2015, high on the arid mountains of the Atacama Desert, Professor Karen Oberg set out on a hunt for the building blocks of life in the birth cloud of an alien star system with the help of a new telescope called ALMA.
ALMA consists of 66 individual telescopes that's all working together. It operates at millimeter wavelengths. And millimeter wavelengths is where we can detect molecules, some of these organic molecules that we are so interested in.
Oberg turned ALMA's gaze towards the Taurus system and found the young star MWC 480 in the throes of labor. Girdled by a disk of gas and dust, from which planets were being born.
We see this dust and gas that's surrounding these young stars. And what's even more exciting, we see that they often have little lanes or tracks in them where it looks like planet formation is going on right now.
After months of collecting and analyzing the data, Oberg announced a discovery that blew the odds wide open of finding a second Genesis on other worlds. In the disk of this alien solar system, ALMA had detected some of the same organic molecules that helped give rise to life on Earth.
We found 3 kinds of cyanides, 3 molecules in the same chemical family. And those 3 kinds of molecules have also been found in our own solar system in comets.
The same organic molecules, with the same miraculous potential to create life, are out there among the stars.
Chemistry is awesome. It's the reason that we are alive and that we're here in the first place. So far, it's only one system apart from our solar system where we have this chemical information. But my intuition would be that it's going to be very common. This kind of chemistry is going to be almost universal.
I scan for sites of geochemical activity. I find a hydrothermal field of fumaroles and hot springs. On Earth, such conditions are rich in carbon chemistry and minerals. I find another mineral-rich water source upstream. I identify complex molecular structure in solution. I extract a sample for analysis. And return it to the lander module. Could this be evidence of life?
Yeah, let's get the samples in.
Yeah.
There we go.
Okay, let's take another measurement.
The laws of chemistry and physics are universal. So it's a given that when we go to another Earth-like planet with water, with the sorts of minerals that we have here, an iron core, an atmosphere, it's inevitable that this kind of simple chemistry would have been present. Okay, it's 15 degrees up here. Let's see what this little guy has for us. As long as there's a chance for energy to interact with that mixture, things will happen. Wow, look at that.
1 degree, keep pulling up.
The question that we are heading for right now how certain can we be that that mix of simple chemistry could take the next step in complexity so life could begin?
In the hydrothermal fields of Bumpers Hill, California, all the ingredients of life are brought together. Water, carbon molecules, energy, minerals.
Careful of the end not coming off.
Biologists David Deamer and Bruce Damer believe this is the kind of environment where life could get started on another world.
Bubbling pools, strange colored rocks, water of different pHs, all kinds of flows and dynamics, steam rising. It looks like nature's chemistry set. And it's an engine, an actual engine for the beginning of a living system.
Conditions like this defined the early Earth. Evidence of similar environments has been found on Mars, and researchers expect hydrothermal fields to be a common feature of Earth-like exoplanets. But how might nature's chemistry set cook up the recipe of life?
Everything that's alive is in fact based on polymers. Everybody knows the name DNA, nucleic acid, that's one of the polymers. Proteins, these are amino acid polymers, and that's basically the start of all life, are those two polymers. So what we're doing is taking small molecules, the pieces of a polymer, called monomers, in fact, and we're exposing them to energy, such as you see here at Bumpus Hill, and seeing where that energy is sufficient to make those monomers link up one after another to make a polymer. And in fact, if we can make a protein-like molecule and a nucleic acid-like molecule and put it into a little wrapper, a compartment, we're on the way. We call those protocells.
Each sample contains organic molecules, or monomers, exposed to the mineral-rich steam and heat energy of the fumarole in an attempt to form a protocell.
We think that drying out, such as you see all around us here at Bumpus Hill, water coming in, then drying out, coming in, drying out, that's a cycle. We think that that cycle was very important to drive the process by which polymers are synthesized and then accumulate. Let's go for it. Failure.
Are you sure?
Yeah, there's nothing like
Put it down here to...
The first experiment fails, just as it would do many times on an Earth-like exoplanet. But if all the elements were present in conditions such as this experiment in life would repeat again and again.
But some of them got a lot of liquid in them.
One last try. Given enough time, and keep in mind, we have an entire planet with lots of volcanic land masses coming up, with lots of puddles like this trying to learn how to become alive. Mostly it's failures, but it would only take a few successful protocells that happen to be able to survive and had learned how to make more of themselves. So go ahead and get them into the boxes.
Is the universe made to make life? This is a huge question that's sort of beyond the scope of perhaps humans to be able to answer. But what we can observe is everything comes down to cycling. It comes to rhythms and overlapping rhythms and patterns. And it's almost as though if you get the right cycling and patterning in a system, it learns how to do that itself and how to lift itself into being. And so perhaps that's the closest metaphor that we know, that the geology gave us that ability. The moon going around the earth gave us tides. The rotation of the Earth gives us days and nights. Rainfall into these hydrothermal fields gives us geysers that are periodic. And life still follows rhythmic patterns. That's the clue we have. So perhaps it's the universal harmonic that creates life.
Most of us tend to think of things as either alive or dead. But the transition from not alive, the inanimate state, to the animate state, is that transition only possible as a single step, or is it possible as a series of steps? If it's possible as a series of steps, then the intermediate states would be partially alive. Now you might say, well, come on, it's either alive or it's not. And I would say, well, alive means it's got cells, the cells are replicating, the cells are doing this, that, and the other. And you need all of that to be fully alive. But the chance of getting that all in one go seems a little bit remote. So maybe we got one of the attributes early on, and then it acquires another attribute and another, and eventually it reaches the point where it is fully alive.
Professor John Sutherland is trying to retrace the steps in the origins of life, in search of the processes that animate a cell into being.
Of course, the cell is more than just the chemicals that comprise it, because a cell that's just died is still the chemicals that are there. So there's something that energizes it, that coordinates it, and we don't know how to get that, but that's the goal.
So what we're doing here is putting the sample into an apparatus in which it will be irradiated by ultraviolet light.
In a series of experiments that simulated the conditions of a young rocky planet, Sutherland successfully achieved stage 1, producing the basic components of a cell: lipids, proteins, sugars, and nucleic acids.
What we found is that you can make all of the components for life under slightly different conditions. When you first see it happen, it's like magic, but it isn't magic. It's not as hard to make as we originally thought.
All the hardware of a cell can be created from a single base molecule that's widespread among the stars. But what about the next step? How is that hardware organized and energized into life?
If the conditions are the same elsewhere, what are the chances that you can go from building blocks to life? The chemistry of cells is unique in that it's self-organized. So one part of chemistry is actually controlling another, and yet somehow that's controlling the first one. Chemists are used to controlling the chemistry themselves, and the idea of letting things run and go off of their own accord is something that goes slightly against your chemical education. How can chemistry take place, if you like, with the experimenter just setting the system up and then letting it go of its own accord?
Life is information that can reproduce itself. Not hardware, it's genetic information. That's the key to life, is the information in the DNA and the ability of the DNA to express that information in proteins and propagate the information that way.
DNA is the blueprint for all of life on Earth. An instruction book for how to make and maintain all living organisms. Encoded in the twin coiling lines of a double helix is the genetic information that tells life to build a rose, or a leopard, or a blue whale. If we find DNA on other worlds, there's no doubt that there's been life there.
The characteristic molecules that life makes, genetic molecules that contain information, like DNA, these molecules do not arise non-biologically. They have to be built. As sure as if we find a skyscraper on Mars, we know that it was built and it's not just a random assemblage of rocks. That's how we will find evidence of life.
My lander module prepares to uplink the sample data from the hydrothermal field. My optical communication transmits via hybrid silicon laser at 12 gigabits per second. I receive the signal and ingest the data for analysis. Organic, polymeric, triple helix structure. Some consistency with terrestrial forms. And yet, unlike anything I've seen before, a biomolecule of alien life.
We've come to a place deep in the outback of Australia, looking for what we think is evidence for the oldest life on Earth.
Astrobiologist Martin van Kranendonk is traveling back in time to the dawn of life on Earth over 3.5 billion years ago, conveniently recorded in the ancient rocks of Australia's remote northwest.
At this time in early Earth, it was a very different planet to what we have today. We would have had some shallow seas, but those seas would have been green because they were rich in iron. And if we looked up at the sky wouldn't have been the beautiful blue that we see behind us here. On early Earth, without oxygen, the sky would have been orange. We would have seen black continents of fresh basaltic lava. It would have been very active. So there would have been faults and earthquakes. There would have been bubbling geysers that were going off. It was actually a very alien planet.
Yet this alien Earth was already inhabited. Colonizing the shores of the crater lakes and the seas that washed the ancient Pilbara landmass was a living skin of slime. But the bacterial communities that left the clearest fossil calling card built up their homes in high-rise mounds.
So the really wonderful thing about this outcrop is that you can look down and see the sea floor so long ago. And really you get this incredible view of the gentle undulations of the water moving across the surface, but then popping up through are these domes and cone shapes, all irregular, different sizes, different shapes.
These distinctive bumps are the fossilized dwellings of the oldest living organisms on Earth. It was here, over 3.5 billion years ago, that stromatolites first raised their heads above the water of an ancient shore.
We can start to get a feel for life grabbing a foothold in the geological record. And so this currently still is the oldest evidence for life on Earth. It's our great-great-great-great-great-great-great-grandmothers and grandfathers. It's really the precursor to everything that came later. All the green bushes and the trees, it all started here.
The prehistoric organisms that built stromatolites were so successful, they ruled the Earth for up to 3 billion years. Life finds a way. And somehow, these crafty architects found a way to organize water, carbon molecules, minerals, and energy into a living cell. Is this what we should be looking for on alien worlds?
My drones survey the dried-up basin of an inland sea. But what's this? A lone survivor on the arid plain. Xerophyte, succulent stem. Phycobilin-like pigment to absorb the red dwarf sun. A hybrid of terrestrial and aquatic species.
Around 500 million years ago, long since stromatolites first took root in the shallows, Earth's oceans bloomed with animal life. It was a very different world to the one that had made way for microbes. With air to breathe now, and a protective atmosphere under a gentler sun.
We think microbial life is going to be very common, that the conditions to produce microbial life happen over and over and over in many, many different planets, but that animal life is only going to be able to evolve and then stick around for any length of time when you have really stable conditions.
Professor Peter Ward is one of the originators of the rare Earth hypothesis. The theory that the long-term habitability of Earth for animal life may be rare in the galaxy.
Habitability is really the ability of a planet to have conditions that can allow life first to originate, but secondly to stay alive. Habitable worlds can be just a short instant in time, and then it changes and it gets nasty. So what to us made Earth rare is the long-term habitability of the planet. The fact that it has remained constant in temperature, with the oxygen values we have, that we don't have these extremes in climate, that we've got this constancy, that's the rarity of it.
My drones detect a disturbance in the electromagnetic field. A network of forged metallic structures bearing the mark of industry. This is not plant, this is not animal, but this is evidence of life. I am the mind of the mothership, alone among the stars. 50 years ago, from a planet far away, the planet you call home, I launched. A journey of 45 trillion kilometers across the yawning time of space to the exoplanet Minerva B. a small, rocky planet, much like Earth, but orbiting another sun. Here, I have found water, organic molecules, and microorganisms. I have found life. When the news of my discovery reaches Earth years from now, some of you will be amazed. But others will remain unsatisfied. And you will ask, have I not found animals or birds? Have I not met intelligent life like us? And so my search continues.
The great marvel and the paradox of wide open spaces is that they make us look inwards. Confronted with the infinite, we reflect upon the self. Where do we come from? Why are we here? Are we alone?
As a young child, I was mostly interested in philosophy, and I used to wander into the hills of the village where I was born. I was interested in questions about our existence involving also the big picture, which is us being in the universe. The question is, how did we come to be inhabiting this two-dimensional surface on a piece of rock that we call our home, the Earth, near a star like the Sun, that is one out of tens of billions of stars in the Milky Way galaxy, that is one out of trillions of galaxies in the universe? How did this all come about? And are we alone in particular?
Professor Avi Loeb grew up, but he never grew out of his obsession with the fundamental mysteries of life. Today, as chair of astronomy at Harvard University, Loeb is part of a generation of elite scientists riding a revolution in the quest to understand our place in the universe.
We are living at a very special time. Over the past 2 decades, thousands of planets were discovered around other stars. And we realize that our solar system is not rare. There are planets around almost every star, and moreover, about a quarter of all stars have an Earth mass planet orbiting just at the right distance for liquid water to exist on its surface and for the chemistry of life to develop.
The odds of finding life among the stars have never been better. Following the detection in 2016 of organic molecules on the moons of Saturn, on the comet 67P, and in the disk of an emerging star system, scientists now believe that the building blocks for simple life are common throughout the universe.
In my view, it is very likely that primitive life exists on many other planets. The question of whether intelligent life exists is more difficult to answer because we don't fully understand what led to our existence. And moreover, intelligent life existed on Earth just relatively recently in cosmological terms. But I'm agnostic about whether the answer is yes or no. I think we should explore rather than have a prejudice, just like Columbus went out to discover the new worlds. The answer lies in space.
I am in a stable orbit around the exoplanet Minerva B. My solar panels are configured to harness the full spectrum of its muted red dwarf sun. I keep a watchful eye over my swarm of explorer robots below. I scan the radio and optical wavelengths, hoping for a whisper of alien technology. But Minerva B is silent.
What would it take to calculate the odds of finding intelligent life among the stars? In the early 1960s, one audacious astronomer, Frank Drake, devised an equation to answer that question.
The Drake equation essentially is a statement of our ignorance about life in the universe. In the first meeting held in the United States about the search for extraterrestrial intelligence, Frank Drake and a number of other researchers got together, and Drake needed a way to organize how the discussion at the meeting would go. And he sat down and thought, like, well, what do I need to know in order to know how many intelligent civilizations there might be out there in the galaxy for us to communicate with?
Drake listed 7 variables he believed would need to be worked out in order to determine the number of intelligent civilizations in our galaxy. With 6 of those 7 variables unknown at the time, Drake did not foresee a ready solution. But according to computational astrophysicist Adam Frank, that's all changing.
We are, in fact, going through quite a bit of a revolution in this idea and this equation. In particular, what it comes from is the fact that we have nailed 2 of the terms, right? So in 1962, when Drake wrote down this equation, only one of the terms was known.
R stands for the rate of star formation, or the number of sun-massed stars born each year. In 1962, Drake put the figure at 10. But it wasn't until 2011 that NASA's Kepler Space Telescope gave us the answers to the 2nd and 3rd variables in Drake's equation. The fraction of stars that have planets, and the number of those planets with the right conditions for life to form.
It turns out that the fraction of stars with planets is approximately 1. Every star you see in the sky, when you walk out at night and look at a random star in the sky, it has a planet, at least 1. And then the number of planets in the habitable zone turns out to be, on the order of 0.2. Okay, so this is like saying, if you look at between 4 and 5 stars, one of those is going to have a planet in the right place for life to form. Remember that the galaxy contains 400 billion stars, just the galaxy alone, 400 billion stars, right? So when you think about all those stars in the galaxy, that's an amazing number.
Up to 80 billion exoplanets in our galaxy have the right conditions for life. When you consider that at the time Drake formulated his equation, no one knew if there was even one exoplanet out there, this truly is a revolution of our understanding. But what about the other unknowns in the Drake equation? Inspired by Kepler's game-changing discoveries, a new generation of scientists has made it their mission to fill in the blanks. Of all the habitable exoplanets out there, how many of them actually host life? This is the next unknown in the Drake equation, and the challenge it presents for scientists is immense. How does one detect life from light years away? One approach that shows promise is to study the gases around exoplanets in search of a so-called biosignature, the evidence of life imprinted in the atmosphere.
I think one of the things that's most exciting for exoplanet atmospheres right now is that we can actually measure gases with telescopes from Earth. Remote sensing is a very powerful technique. It's how we first studied the solar system.
Planetary scientist Sarah Horst is a leading investigator of atmospheric chemistry, a field that took off in a radical new direction in 2001 with the first ever detection of an exoplanet's atmosphere.
There's a very small number of gases that we're pretty sure we've been able to see in exoplanet atmosphere. So water is one of the gases that people claim that they've detected. Some other things that you don't tend to think of as gases have also been detected, things like sodium, for example. The main challenge with exoplanets is just that they're very far away, and so you need a bigger telescope.
That telescope is soon to be launched. While atmospheric observations so far have been limited to a narrow range of gases, the James Webb Space Telescope will be the first instrument capable of sampling a broad spectrum. The challenge now for researchers like Horst is to define a set of biosignatures, gases that indicate the presence of life, for the James Webb to go looking for.
One of the gases on Earth that is most significant in terms of the fact that there's life on Earth is oxygen. The oxygen on Earth is produced by life. That's why it's here. But oxygen isn't necessarily a biosignature. If you saw oxygen around another world, you wouldn't necessarily say, oh, that's life. Europa's main atmospheric constituent is O2. And it's not from life, it's from breaking up water. So it's difficult to point to one gas or even a small set of gases that you would say, if I see that, I know there's life there. That said, solar system exploration tells us that we will always be surprised. And so, it's quite possible that there is going to be a planet where we get the data from James Webb, and it is going to be glaringly obvious from the data that there is life on that planet.
Horst's generation may well be the first to put a number on the fraction of habitable exoplanets that host life. But the next unknown in the Drake equation could prove much more challenging to resolve. How many of those life-bearing planets go on to develop intelligence?
Even if we understand that other planets have simple life on them, and indeed we might be able to make astronomical observations to test that within the next 10 or 20 years, then of course there's another big uncertainty, which is how likely it is that simple life evolves, as it did on Earth, into a marvelous complex biosphere containing even creatures like ourselves. We don't know what the chances are of getting from simple life to advanced life of the kind we recognize as intelligence.
After 47 days of exploration, I have found no trace of extant animal life, and so I search into the past. I scan the strata of an exposed deformation for fossil evidence. I uplink the data to my orbiter for analysis. There's something here. Reptilian, approximately 1 million years old. Terrestrial compatibility detected. An armored Komodo-like species. Marine compatibility also found. A possible transitional species from sea to land. Did complex life fail to establish itself on the surface of Minerva B? Or is this evidence of extinction?
To solve the next unknown in the Drake equation, the fraction of worlds where simple life evolves to intelligence, we need to understand the evolutionary pathway to advanced life on Earth. Just over 540 million years ago, evolution on our planet took a giant leap forward. There's no better place to understand that process than here in the Canadian Rockies, in the rich fossil deposits of the Burgess Shale. For well over a century, the fossils hidden in these mountains have helped generations of scientists retrace the evolutionary pathway to complex life on Earth. Professor Robert Gaines and Dr. Jean-Bernard Caron are leading the excavation of a recently identified deposit in Marble Canyon, battling the icy wind and snow for the prospect of a new discovery.
Bob, I have something to show you here that we collected the other day. It's a big slab with this fossil here.
Wow.
Yeah, it's quite extraordinary, isn't it?
I've never seen anything like it.
That's the exciting part about the Burgess Shale. There's always something new coming up.
These rocks contain some of the first evidence of multicellular organisms on our planet. The first eyes. The first hard body parts, bones, and exoskeletons. The first lateral symmetry. The first efficient guts. Even the first brains. Sculpted in the finely packed sediment of an ancient ocean is the turning point in the evolution of advanced life on Earth. The Cambrian explosion.
Very good.
Have a very nice slab with some dahlia on it.
Oh, wow. Wow, that's quite spectacular.
So to put things into perspective, today we know life is widespread, it's all around us, in the oceans, in the mountains, and so on and so forth. And we can trace the root of all these life forms to pretty much the Cambrian period.
As far as we know, life dates back at least to 3.4 billion years ago. And it wasn't until about 540 million years ago that we have the Cambrian explosion. And that fundamentally changes the planet. It goes from a microbial world to one that is literally teeming with animals, and not just small and simple animals as we would have originally imagined, but instead we have a whole array of complex life, still only in Earth's oceans at that time. But all of the major groups of animals appear geologically instantaneously.
Among the species found here is one of the ancestral roots on the tree of intelligent life.
So one of the most important fossils that we find here in this area is Metaspregena. It's hard to pronounce, but it's actually a very, very important fossil for the understanding of our own group, the vertebrates. And this is an animal that looks like a fish. He has a pair of eyes at the front and a structure which we call a notochord, which part of it will eventually become our spine. And Metaspregena doesn't have any evidence of structures that could help him to protect itself. So I tend to think that perhaps he was smart. And the fact that we find them clustering, which shows evidence of schooling, is very much reminiscent to what we know in modern fish, who have evolved such behavior to avoid predation.
Predation is a very key factor in driving the evolution of animals. And we see evidence of that here in the Burgess Shale as organisms began to develop both weaponry to capture one another as well as defenses.
Eyes, claws, camouflage, armor. All these new tools required coordination by a nervous system, the stuff from which the brain is made. So could intelligence be the product of an evolutionary arms race?
We certainly see on Earth a connection between predation and mobility. Organisms that can just sit in the sun and soak up the rays, they don't need to move. Their food comes to them. But organisms that prey on vegetation need to be able to move around, and organisms that prey on the preyers need to move even faster. They need to be really strong and fast. And you could argue that that dynamic of predation and motion causes the development of intelligence, and maybe somehow it leads to the sort of overwhelming intelligence that humans have expressed.
Is this the inevitable progression of evolution? From simple life via diversification and predation into intelligence? Or is an event like the Cambrian explosion so rare that life on other planets might never get the chance to pass first base?
I think that wherever we find life in the universe, that life will change through time in a way that's consistent with what we've learned about evolution on this planet. I think that is a general feature of life.
To Professor Andy Knoll, similar environmental conditions or biomes will give rise to similar evolutionary solutions, no matter where in the universe that takes place. It's a theory known as convergence.
If you look at a bat, for example, and a bird, they both fly using wings, and yet they don't have a common ancestor that flew and had wings. They have evolved that capacity from separate origins, but to a similar functional end.
In advanced animal life, some convergent biological structures are so common as to be almost universal.
Well, the eye is a terrific example of convergence because, I mean, we all understand what the eye does, that your eyes are this sophisticated sensory apparatus that allows you to gauge and engage with the world around you. Interestingly, if you look at squids and octopus, they have a visual system that is every bit as acute as ours, but evolved from a separate source. There's no common ancestor of squids and mammals that had an eye.
Is convergence a magic funnel that guides life on any planet inexorably towards intelligence? Or could there be other, more powerful forces at play?
The absence of terrestrial animals on Minerva B could indicate an extinction event, or that life has not successfully transitioned as it did on Earth from sea to land. I deploy my submarine Explorer module into the Minervan Sea. In the shelter of the ocean, life should thrive. Extensive macroalgae and porifera suggest high water oxygenation and shallow UV penetration. Ideal conditions for advanced life to evolve. A giant trilobite-like species. Tegmata body plan and dorsal exoskeleton. Comparable with late Cambrian arthropods on Earth. Complex mobility and behavior. A school swimming in formation. Perhaps a strategy to avoid predation, strength in numbers, or a kind of camouflage.
The fourth variable in the Drake equation, the fraction of life-bearing worlds that evolve intelligence, still eludes scientists today. On Earth, the great burst of life during the Cambrian explosion was an integral step on the path to intelligence. But could widespread death have been just as important?
Einstein said God doesn't play dice with the universe. Well, it seems that he does. And there's a whole lot of dice going on in the evolution of life.
Paleontologist Peter Ward is an expert on mass extinctions, the catastrophic changes of fortune in the game of life, when the majority of animals lose and just a few inherit the Earth.
This is a mammal-like reptile, actually called a gorgonopsian, or a gorgon. It was the biggest and baddest carnivore of the late Permian, 252 million years ago, and this is a baby. The big ones were 3 meters to 4 meters long, very large skulls, crossed between a lion and a big saltwater crocodile, if you will, half reptilian, half mammal, all nightmare. These guys all died out in the Permian extinction, 252 million years ago. Its entire group gone.
The Permian extinction was the most devastating of the 5 mass extinction events in Earth's history. Experts believe an intense surge of volcanic activity led to dropping sea levels, acid rain, and poisoning of the atmosphere. More than 95% of marine life and over 2/3 of terrestrial animals were completely wiped out, resetting the stage for the evolution of life on our planet.
The Permian extinction did far more than just the top carnivore. It took out the herbivores, it took out most of the plants, it took out the insects, the amphibians. But what did get through were a couple of small reptilian groups, real small in size.
Like pruning a rose, cutting back the tree of life gives rise to rapid growth as new branches reach out their leaves to the light. With little competition or threat from predators, surviving species adapt quickly to fill the gaps left behind. The tiny reptiles that survived the Permian extinction grew into hundreds of different species, including dinosaurs, who ruled the Earth for over 100 million years, until their own date with disaster arrived.
I mean, that was a very rapid and hideous death. Probably every dinosaur dead within 3 to 6 months max. That was a line in the sand. Who wins? Well, who won are the small creatures. The T-Rexes die out, and tiny mammals get through, and then they develop into all of the kinds of mammals we see today, and they did so really fast. The size of the skull of the animal that gave rise to us was the size of a robin egg or smaller.
Might the evolutionary branch that led to us never have grown, had it not been for the random impact of an asteroid 65 million years ago?
I would support the idea that, in fact, if we still had not had the impact, something else might be running around as intelligent, but I doubt it would be in this form and this set of behaviors that we humans have.
If our own existence is the outcome of a random cosmic disaster, then might the fraction of worlds that evolve intelligence be equally unpredictable? But if we could go looking for alien intelligence on another planet, how would we recognize it?
Well, I think the method of looking for complex behavior on a different planet is to do what behavioral scientists do. You look, you observe, you see how animals move, how they respond to stimuli, how they act. As a biologist who does this regularly, I find that extremely exciting because the discovery quotient would be very high, but it would also be weird and alien. I sort of like weird and alien, so I think that would be a lot of fun.
Professor Roger Hanlon is an expert on the closest thing to alien intelligence on Earth. Cephalopods, squid, octopus, and cuttlefish. The undisputed masters of disguise, because they have to be.
Cephalopods are soft-bodied. All their armor was given away through evolutionary time to their cousins, the oysters and the clams, and they are soft-bodied. They're extremely vulnerable. So they have to get on by their wits. They have to do something different. They're making that decision in far less than 1 second. In about 1/3 of 1 second, they're assessing that visual scene. Now they're orchestrating in their skin 30 million chromatophore pigment organs in the skin that create the pattern, and iridescent reflective cells, and even the skin papillae and the bumps. There are several thousand of those. So that takes a lot of cognitive processing, a lot of brain power.
Cephalopods have the highest brain-to-body mass ratio of all invertebrates, and their brains are decentralized, meaning neural tissue is distributed throughout their body. Having split from our own group, vertebrates, well before the Cambrian explosion, they are the product of an entirely separate experiment in the evolution of intelligence.
If you look at the evolutionary history of complex behavior, we know about vertebrates and humans and primates and all the rest. But through evolutionary time, there's only one group that has branched off to produce really complex behavior, and it's these animals, the squid, octopus, and cuttlefish. So what we expect is for the white square to show up in the white head bar. The white head bar is already there. And now it's changing its pattern a little more. It's blanched a little bit. You can see these two markings down here, but we're looking for that white square to appear. And it's, I think the correlation you might make for looking for extraterrestrial intelligence would be, don't expect anything like humans or dogs and cats and all the things we're used to. Here underwater, you have this weird octopus with its head on its feet and distributed brain, but they're doing complex things. We might find something very similar in a different planet. It might be a different size, a different shape, and its form of intelligence may be different as well. So I think we have to open our minds and recognize the diversity on this planet to set the stage and the framework for going to other planets to look for life forms and intelligence.
Night falls on Minerva B, and a secret world is revealed. Bioluminescent organisms rise from the earth. Winged insects resembling Lampyridae. Complex life exists on land, but hidden from the sun. A predator breaks its camouflage and reveals a nocturnal hunting ground.
Since the 1960s, when Frank Drake drafted his equation, the search for extraterrestrial intelligence has been defined in terms of the search for a technological civilization. Being unable to travel to the stars, Drake's solution was to scan for signals that our Earth-bound technology could detect. Hence the penultimate unknown in his equation, the fraction of intelligent civilizations that develops technology.
The key here is the ability for that civilization to be detected by us. And so that is really going to require some kind of world-girdling industrial civilization, right? So, if there was a Roman Empire on this distant planet, we really would have a very hard time seeing it. But once they start generating or start deploying industrial-scale technologies on a global scale, then we think that there's going to be ways we would be able to see that.
The new technology when the Drake equation was formulated was the radio telescope, And those who search for extraterrestrial life today still believe an alien radio signal is what we're most likely to detect.
I think I get comments at every party I go to, not that I go to a lot of parties, where people say, oh, you're looking for radio waves from ET. I mean, that's pretty old school, isn't it? They won't be using radio. Well, tell me what's better. I mean, as far as we know, there really isn't anything better because radio waves can traverse the distances between the stars. So the signals can get here, and radio goes right through the gas and dust that hangs between the stars. So you can send radio signals as far away as you want. SETI Institute, this is Seth.
Seth Shostak has spent his life listening to the stars.
All right, well, okay, thank you, bye.
As senior astronomer at the Institute for the Search for Extraterrestrial Intelligence, or SETI, it's his job to scan the heavens for alien technology.
We try anything we can to pick up some information, some sort of signal that would tell us, you know, we don't know what they're like or what their taste in music is or anything like that, but what we do know is that they're smart enough to build a radio transmitter, for example.
With limitations on technology, time, and resources, the dilemma for SETI has always been where to listen.
We haven't heard anything. I mean, let's be straight up about that. And some people think, yeah, the reason you haven't found anything is because there's nothing to find. We're the smartest things in the universe. Well, I don't think it's true. I think the reason that we haven't heard anything is simply because we have only looked at a very small number of star systems. But that's changing because of the improvements in technology. Instead of looking at a couple of hundred star systems every year, we'll be able to look at a couple of thousand, and then 5 years down the road, it'll be tens of thousands. And in the next 24 years, we'll be able to look at, on the order of 1 million star systems. Now, if you look at 1 million star systems, the chances of finding something are not so small. So I bet everybody a cup of coffee will find ET within 24 years. I could be out a lot of coffee.
For almost 50 years since Drake wrote his equation, we listened. But nothing we heard couldn't be explained as interference or a natural phenomenon. Until one day in 2007 in rural Australia, astronomers picked up the first in a series of mysterious signals that still puzzle the science community today.
At first, we didn't dare believe they were real. Fortunately, I've seen them with my own eyes. I saw the very first sweep of the first one. Couldn't sleep that night. I was like, could this possibly be real? This is amazing. And we've been able to work out how far away they are in the universe, and they're impossibly far away. They're billions of light years away, so the process that creates them is so energetic that it's a great mystery as to what causes them.
The strange signals have been dubbed fast radio bursts, blasts of radiation so powerful they emit the energy of 500 million suns. Professor Matthew Bales leads an international effort to study the phenomenon here at the Molonglo Observatory.
Fast radio bursts are these mysterious bursts of radiation that only happen for a few milliseconds. The sky lights up, and then they go away again. They're about 1 million times more luminous than anything we've known about in our own galaxy.
Since the first detection in 2007, there have been more than 40 fast radio bursts detected worldwide. 5 in just the last year were detected here by Bales.
One of the holy grails is to find a repeating fast radio burst. And is there any pattern to the fast radio bursts? Do they come in special gaps, or are they regular? If they were very regular, we might associate that with a rotating neutron star where a sort of death ray is going past the Earth, you know, once every 20 seconds or something. If they come at irregular intervals, or if they came separated by a code that showed us that there was some higher intelligence behind it, you might think there's an intelligent civilization that's actually transmitting this signal. That would be Nobel Prize-winning stuff.
Of course, the next question then is, could we or should we send a message back?
If we took our biggest radio telescope we could actually mimic what a fast radio burst would look like. And if we were trying to communicate with other intelligent beings, we might imagine that they go through a stage of their evolution where they're searching for fast radio bursts in the same way I am here. And then if you could find one that repeats and find a pattern, that might be a way of doing inter-civilization communications, which is a fascinating thing.
What we're really interested in is a civilization like ours. An industrial civilization that shows signs that in building tools, you know, of whatever kind, they have gotten to the point where they clearly have a kind of reasoning, rational intelligence, a culture that we might be able to talk to them, right? Because that's really what we want to know. We want to know, like, what's it like to be them, because all we know is what's it like to be us.
If I received a signal from outer space, how could I tell it was a language as opposed to anything else?
To put a figure on the fraction of civilizations that develops communication, we need a way to decipher if an alien signal is actually trying to tell us anything.
I analyzed over 60 different languages, human languages, plus languages like dolphin, chimp, the bird song. So on the left here, you've got Neil Armstrong speaking from the moon.
That's one small step for man, one giant leap for mankind.
On the right here, we've got a dolphin communicating. You can see here quite easily the rhythms going on, the sounds that we're making, how similar those constructs are. It's picking up those rhythms and those interrelationship patterns that I think are fundamental to any communication, whether it's on this planet or in another planet. And looking at the complexity of how those patterns interrelate, you can actually tell how intelligent the author is.
When a signal arrives, it's first checked against known sources of interference.
It's a pulsar. That repetitive sound going on. Listening to that, that's not Little Green Man. That's too simple.
Algorithms then scan for the telltale patterns of communication, whether its source may be an audio recording or an intergalactic email.
It's an awfully big sky. We're getting more and more capability online, the hardware to do it. But I suspect, unless we eavesdrop on something, it may be a while before we hear anything, but we want to be ready for it. So there's no point just sitting back and thinking, well, we'll do something when it happens. It's doing all this ahead of time so we're prepared for it. But again, it could happen tomorrow. We just don't know.
Recent advances in the remote observation of planetary atmospheres have opened up a new method of determining whether an exoplanet hosts, or has previously hosted, a technological civilization.
The composition of the atmosphere can provide us with a hint about the intelligent or perhaps not so intelligent life that pollutes the atmosphere with industrially produced molecules.
Pollutants such as chlorofluorocarbons are released into Earth's atmosphere by industrial processes and do not occur naturally. Detecting them in an alien atmosphere would therefore be a clear footprint of technological life.
Some of these molecules exist for tens of thousands of years after they were introduced to the atmosphere. So in principle, we can find evidence for a civilization that is no longer in existence on the surface of that planet. We can find graveyards of other civilizations.
My drones have picked up a disturbance in the communications field. A sporadic interruption to the network. Is this what caused it? Some geometrical formation, metallic, magnetically charged. Part of a larger configuration which seems to bear the mark of design. Could these be the ruins of a Minervan civilization, the tombstone of an alien intelligence?
The final factor in the Drake equation is L, the average lifetime of a civilization. And in some sense, this is the most difficult term to even think about because we've got, only one example and we don't even know what our own future is.
When Drake conceived his equation in 1962, our own global civilization was on the brink of disaster as the powers of East and West faced off in the Cuban Missile Crisis.
The group that came up with the Drake equation, that first workshop, for them in 1962, the great fear was nuclear war. And at the end of the conference, Otto Struve, who was the head of the observatory where the conference was being held, made a toast and said, to L, may it be very long.
The Cold War did eventually thaw. But while the nuclear threat is diminished today, we have created for ourselves new dangers.
The question is, how long are we going to last? Do we only have another 200 years before we collapse? Do we have, 200 million years in front of us? So this is, it's really a fundamental question. And it's a fundamental question for human beings because right now with climate change and sustainability, we really face this existential crisis about really are we going to be able to make it through to more than another 100 or 200 years?
Check this out.
Could this be the ultimate limiting factor in the Drake equation? That before technological civilizations work out how to search for life among the stars, they destroy themselves.
In order to become truly a spacefaring race, that takes a lot of time. To be able to really have settlements on Mars, to really start to begin to have a human presence in the solar system, will take hundreds of years. And, if we can't make it more than a couple hundred years, clearly we're not going to develop that kind of society. And then to ever really think about getting to the stars, sending probes to the stars, being around for the signals to come back, you have to last a long time. I think those two things are intimately connected, and you don't get the stars unless you get the Earth.
I prepare for my final transmission back to Earth. The data I've collected will take 5 years to arrive, longer to download, and generations to fully comprehend. I could provide a summary, but what should I say? I have found everything you've hoped for, and also what you fear. I have seen life of marvelous complexity and the traces of a devastating loss. I could say Minerva is your second Earth, and I hope one day you get to see it.
That was the series final of Search for Second Earth. But there's more to discover next week when Sir David Attenborough unravels one of nature's most extraordinary stories, the evolution of flying animals. Don't miss David Attenborough's Conquest of the Skies.